Imagine looking up at the night sky, knowing that somewhere out there, orbiting an alien world, is something humanity has never seen before, a moon beyond our solar system. We've discovered thousands of exoplanets, but what about exomoons? Do they even exist? And if they do, why haven't we found one yet? Well, the truth is, we might have. But the search for the first confirmed exomoon is filled with mystery, uncertainty, and even controversy. For decades, astronomers have dreamed of finding moons around distant planets, but the problem is, exomoons are incredibly hard to detect. Unlike exoplanets, which cause noticeable dips in the light of their stars when they pass in front, exomoons are much smaller, making their signals faint and difficult to distinguish from noise. It's like trying to hear a whisper in the middle of a rock concert. But that hasn't stopped scientists from searching. The idea that moons exist beyond our solar system isn't just logical, it's inevitable. In our own solar system, moons are everywhere. Jupiter alone has over 90, Saturn has more than 140, and even tiny Pluto has 5. If moons are so common here, why wouldn't they be common elsewhere? The first real breakthrough in the hunt for exomoons came in 2017 when astronomers found what they believed was the best candidate yet, a potential moon orbiting a gas giant more than 8,000 light-years away. This discovery was monumental. If confirmed, it would change everything we know about planetary systems and moon formation. But there was a problem. The evidence wasn't definitive. Scientists needed more data, and that meant waiting for the planet and its possible moon to pass in front of their star again. Years passed, and astronomers gathered more observations. But instead of confirming the moon's existence, the results only deepened the mystery. Some data supported the idea that an exomoon was there, while other analyses cast doubt on it. Was this truly the first exomoon ever discovered? Or was it just an illusion, an artifact of data processing, or an error in the models used to detect it? The debate raged on, and to this day, the question remains unanswered. But that's just one mystery in the search for exomoons. The truth is, even if this candidate turns out to be a false alarm, the hunt isn't over. Astronomers are developing new methods, improving their techniques, and using more powerful telescopes to scan the cosmos for these elusive moons. If we can find them, we might finally answer some of the biggest questions in science. How do moons form? Could they support life? And what do they tell us about the planets they orbit? The search for the first exomoon is a puzzle filled with twists, setbacks, and incredible discoveries. And in this video, we're going to explore everything we know about it. From the first hints of exomoon candidates to the ongoing challenges in confirming them, we're going deep into the mystery that could reshape our understanding of planetary systems. So let's dive in. The story of exomoons starts with an even bigger mystery: how planets form in the first place. Planets don't just appear out of nowhere. They start as swirling disks of gas and dust around young stars. Over time, gravity pulls these particles together, forming larger and larger objects. But as planets take shape, leftover material doesn't just vanish. Some of it sticks around, forming rings of debris that can eventually clump together to create moons. In our own solar system, we see evidence of this process everywhere. Earth's moon likely formed when a massive object slammed into our planet billions of years ago, ejecting debris that eventually coalesced into a single, large satellite. Jupiter's largest moons formed from the gas and dust surrounding the planet in its early days. And then there are moons like Triton, Neptune's largest moon, which scientists believe was captured from the Kuiper Belt, a region filled with icy bodies beyond Neptune. If moons can form in so many different ways here, the same should be true for exomoons. But the problem is, detecting them is ridiculously hard. Imagine trying to see a single firefly next to a stadium floodlight from miles away. That's what it's like trying to find an exomoon. The first real attempts to detect exomoons began in the early 2000s, when astronomers started using the transit method to find exoplanets. This method looks for tiny dips in a star's brightness when a planet passes in front of it. Theoretically, if a planet has a moon, it should create additional dips or slight variations in the timing of the planet's transit. But in practice, this is much harder than it sounds. Moons are smaller than planets, meaning their signals are weaker. And on top of that, the data we get from telescopes is noisy, filled with interference from the instruments themselves, the star's natural variability, and countless other factors. Despite these challenges, scientists kept looking. Then, in 2017, came the big announcement. Researchers using data from the Kepler Space Telescope had found a potential exomoon orbiting a massive planet known as Kepler-1625b. The planet itself is a gas giant, several times the size of Jupiter, and it orbits its star at a significant distance. But what really caught astronomers' attention was an odd pattern in the planet's transit data. It wasn't a clean, predictable dip in brightness. It had an extra variation, something that hinted at the presence of a moon. To confirm their findings, the team turned to the Hubble Space Telescope for more precise measurements. And when they observed Kepler-1625b again, they found something incredible. The planet seemed to transit slightly earlier than expected, a possible sign that a moon was tugging on it gravitationally. On top of that, there was a second, smaller dip in brightness, just what you'd expect if an exomoon were passing in front of the star as well. The discovery made headlines around the world. If real, this exomoon would be unlike anything in our solar system. It appeared to be enormous, possibly the size of Neptune, and it didn't resemble any of the moons we know. But as with all groundbreaking discoveries, skepticism followed. Other researchers analyzed the data and pointed out possible flaws in the interpretation. Maybe the signal was just an anomaly. Maybe the data processing had introduced errors. Maybe this so-called exomoon wasn't a moon at all, but something else entirely. Since then, the debate has continued. More observations have been made, but they haven't provided a clear answer. The evidence is still inconclusive, leaving Kepler-1625b's moon in scientific limbo. Some astronomers remain confident that exomoons exist and that this was a real detection, while others believe we need more proof before making such a bold claim. But whether or not Kepler-1625b has a moon, the search is far from over. New telescopes, like the James Webb Space Telescope, are giving us better tools to find and confirm these elusive objects. Astronomers are also exploring other methods, like looking for tiny wobbles in a planet's motion caused by a moon's gravitational pull or searching for radio signals that could indicate a moon's presence. The truth is, the first confirmed exomoon could be found any day now. And when it happens, it won't just be another discovery, it will be a revolution in our understanding of planetary systems. Because if we can find exomoons, it opens up a whole new question: could they support life? Some of the most intriguing places for life in our solar system aren't planets, they're moons. Europa, Enceladus, and Titan all have conditions that could support alien life. If exomoons exist around distant planets, they might be habitable too. The possibility of habitable exomoons is one of the most exciting aspects of this search. In our own solar system, moons like Europa and Enceladus are considered prime locations for extraterrestrial life. Not because they have atmospheres like Earth, but because they have subsurface oceans that might contain the conditions necessary for life to thrive. If similar moons exist beyond our solar system, they could provide even more opportunities for life to emerge. One of the biggest challenges in detecting exomoons is figuring out how to separate their signals from everything else happening in the data. Even the best telescopes in the world struggle to see something as small as a moon next to a massive planet. The methods used to find exoplanets, like the transit method and radial velocity, can give us hints that a moon might be there, but they aren't always enough to confirm it. The transit method, for example, relies on watching a planet pass in front of its star, creating a dip in brightness. If that planet has a moon, the moon should create its own dip, but this dip is much smaller and harder to detect. Another technique scientists use is called transit timing variations, or TTV. Normally, a planet orbits its star in a predictable way, meaning its transits happen at regular intervals. But if the planet has a moon, that moon's gravity will pull on the planet, causing slight variations in the timing of its transit. This is one of the key pieces of evidence that led to the suspicion that Kepler-1625b might have a moon. The problem with TTV, though, is that other things can also cause variations in transit timing, like other planets in the system or even errors in the data. There's also another method called transit duration variations, or TDV. This works similarly to TTV but focuses on how long the transit lasts rather than when it happens. If a planet has a moon, the gravitational pull from that moon might make the planet move slightly differently, causing the duration of its transit to change. Again, this method is useful, but it's not definitive proof of a moon's existence. Despite all these challenges, astronomers are getting better at identifying exomoons. One of the key ways they're improving their methods is by using more powerful telescopes. The James Webb Space Telescope, JWST, is one of the most advanced observatories ever built, and it's capable of detecting much fainter signals than previous telescopes. Scientists hope that JWST will provide the data needed to confirm an exomoon once and for all. In addition to JWST, future telescopes like the Nancy Grace Roman Space Telescope and even next-generation observatories that haven't been built yet could make the search for exomoons even easier. These telescopes will have higher resolution and better sensitivity, allowing scientists to detect smaller and fainter objects. But what if we've already found exomoons and just don't realize it? Some astronomers believe that past exoplanet discoveries may have already included exomoons, but their signals were too weak or too complex to be noticed. With improved analysis techniques, we might be able to go back and re-examine old data to find moons hiding in plain sight. One of the most exciting possibilities is that some of these exomoons could be even stranger than anything we've seen in our solar system. For example, what if there are moons orbiting rogue planets, planets that don't have a star? These moons would be drifting through the galaxy in complete darkness, possibly with their own internal heat sources keeping them warm. If such moons exist, they could challenge our understanding of how planetary systems form and evolve. There's also the question of whether exomoons could have their own moons. In our solar system, we don't see this happening because the gravitational forces from the planets they orbit tend to be too strong. But in other star systems, under the right conditions, it's possible that moons could have their own smaller satellite bodies, creating an entirely new category of celestial objects. As the search for exomoons continues, scientists are also asking a bigger question: could these moons be home to life? We know that some of the best places to look for life in our solar system are moons, not planets. Europa, one of Jupiter's largest moons, has a thick icy shell covering an ocean of liquid water. Enceladus, a moon of Saturn, has massive geysers that spew water vapor into space, suggesting a subsurface ocean that could contain the ingredients for life. If exomoons have similar conditions, they could be prime locations for alien life. Some researchers believe that exomoons might actually be better places for life than exoplanets themselves. One reason is that moons can have more stable climates. A planet's climate is influenced by many factors, including its distance from its star, its atmosphere, and the presence of other planets in the system. But a moon orbiting a gas giant might have a more stable environment, protected by the gravitational forces of its planet. Another possibility is that exomoons could have atmospheres and even liquid water on their surfaces. If a moon is far enough from its planet, it could experience Earth-like conditions, with seasons, weather, and oceans. Some scientists have even speculated that exomoons could have dense atmospheres that trap heat, making them warm enough to support life even if they're far from their star. One of the biggest unknowns is whether exomoons could develop their own ecosystems. On Earth, life has evolved in a variety of extreme environments, from deep-sea hydrothermal vents to the frozen tundra of Antarctica. If exomoons exist with conditions similar to Earth's, it's not impossible that life could arise there as well. The search for exomoons is still in its early stages, but each new discovery brings us closer to answering some of the most profound questions about the universe. Are we alone? Do moons beyond our solar system harbor life? And how do these distant worlds compare to the ones we know? In the coming years, new missions, new telescopes, and new technologies will push the boundaries of what we can detect. The first confirmed exomoon might still be waiting to be discovered, hidden in the data we've already collected or in the light of a distant star that we haven't yet studied. But one thing is certain: the search for exomoons isn't just about finding new worlds, it's about redefining our place in the cosmos. The idea that exomoons could redefine our place in the cosmos is not just a philosophical notion, it's a scientific revolution waiting to happen. If we confirm that moons outside our solar system can host life, it would change the way we think about habitability, planetary formation, and even the likelihood of extraterrestrial civilizations. It would mean that we are not just looking for Earth-like planets in the habitable zone of their stars, but also for Earth-like moons that could be just as, if not more, capable of supporting life. One of the most fascinating aspects of exomoons is the possibility of tidal heating. In our solar system, Jupiter's moon Io is the most volcanically active body, and this is due to the immense gravitational forces exerted by Jupiter and its other moons. This constant gravitational squeezing generates heat inside Io, fueling its volcanoes. If similar tidal heating occurs on exomoons orbiting gas giants in other star systems, it could create subsurface oceans, even in places far from their star's habitable zone. This means that exomoons don't necessarily have to be in the traditional Goldilocks zone to support liquid water and possibly life. The detection of exomoons could also teach us more about the chaotic nature of planetary systems. In our solar system, we see moons that have likely been captured from other places, such as Neptune's moon Triton, which is thought to be a former Kuiper Belt object. If exomoons are detected with unusual orbits, retrograde motion, or extreme eccentricities, it could suggest that these moons were once rogue objects floating through space before being captured by their host planets. This would mean that planetary systems are even more dynamic than we previously thought. One of the biggest game changers in the search for exomoons will be direct imaging. Currently, most exoplanets and possible exomoons are found indirectly through methods like transit observations or radial velocity measurements. But as telescopes improve, we might be able to directly photograph some of these distant worlds. Direct imaging would allow scientists to study their atmospheres, compositions, and even weather patterns. It would be a breakthrough that could confirm exomoons with certainty, removing any ambiguity caused by indirect detection methods. Another factor that makes exomoons particularly intriguing is their potential for hosting atmospheres. On Earth, our atmosphere is essential for life because it protects us from harmful radiation, regulates temperature, and provides the gases we need to breathe. Some exomoons, if they are large enough and have the right conditions, could develop thick atmospheres, potentially creating environments where life could thrive. If an exomoon were orbiting a gas giant within a star's habitable zone, it could have stable conditions similar to Earth. This means that the search for exomoons is not just about finding moons, it's about finding entire new worlds that could resemble Earth in ways we never imagined. The discovery of the first exomoon will also raise questions about how moons evolve and whether they can change over time. In our solar system, we see moons that are geologically active, like Io, and others that are essentially frozen worlds, like Callisto. If we find an exomoon that appears habitable, we'll also need to determine how long those conditions have existed and whether they are stable over long periods. If an exomoon was habitable millions of years ago, but has since become a barren wasteland, it could provide insights into how planetary bodies change over time. One of the most exciting implications of finding exomoons is the possibility of interstellar colonization. If humanity ever ventures beyond our solar system, exomoons might be the perfect stepping stones for space exploration. They could provide shelter, resources, and even habitable environments that make deep space travel more feasible. Some scientists even speculate that if advanced extraterrestrial civilizations exist, they might have already colonized exomoons rather than planets, since moons offer unique advantages like stability, proximity to gas giants for energy, and protection from cosmic radiation. But what if we've already seen signs of exomoons and just don't recognize them yet? Some unexplained anomalies in exoplanet data could be caused by unseen moons, but without conclusive proof, we can only speculate. Astronomers are currently combing through years of Kepler data, looking for subtle patterns that might indicate exomoons lurking in the shadows of distant planets. The discovery of the first exomoon will be one of the most significant milestones in modern astronomy. It will confirm that moons are not just an odd feature of our solar system, but a common occurrence in the universe. And if exomoons are as abundant as we suspect, the chances of finding life beyond Earth increase dramatically. Every new telescope, every new mission, and every new piece of data brings us closer to that moment. Whether it happens tomorrow, next year, or decades from now, the first confirmed exomoon will open a new chapter in our understanding of the cosmos. And when we finally find one, we won't just be looking at a moon. We'll be looking at a world that could change everything we thought we knew about life in the universe. The discovery of the first exomoon is not just an isolated event, it's a gateway to an entirely new way of understanding planetary systems. If we confirm that exomoons are common, it would mean that the number of potentially habitable worlds in the universe is far greater than we ever imagined. It would mean that our search for life has been too narrow, focused only on planets when, in reality, moons might be just as promising. But why has it been so difficult to find exomoons in the first place? One reason is that moons are much smaller than planets, making them incredibly challenging to detect with current technology. When we look for exoplanets, we rely on their ability to block light from their star as they pass in front of it, a method known as the transit method. But a moon is much smaller than its host planet, so the tiny dip in starlight it would create is far harder to distinguish from the noise of distant space. Another challenge is that moons don't always transit in a predictable way. Unlike planets, which follow relatively stable orbits around their stars, moons can shift positions due to the gravitational influence of their host planets. This means that even if a moon does transit its star, it might not do so every time the planet does, making it even harder to track. To overcome these difficulties, scientists have been using a variety of innovative methods. One approach is to look for slight variations in the timing of a planet's transit. If a planet's transit happens a little earlier or later than expected, it could be a sign that an unseen moon is tugging on it. This technique, known as transit timing variations (TTV), has been one of the most promising ways to search for exomoons. Another method is to study the slight wobble of a planet as it moves. Just as a planet can cause its star to wobble due to gravity, a moon can do the same to its planet. If scientists can detect a slight, rhythmic wobble in a planet's motion, it could indicate the presence of a moon. There is also the possibility of using gravitational microlensing. This occurs when the gravity of a star or planet bends and magnifies the light from a more distant object. If a planet has a moon, the light distortion might reveal the presence of both objects. This method is still in its early stages, but it could provide a completely new way of detecting exomoons in the future. One of the most exciting developments in exomoon research came with the possible detection of Kepler-1625b I, a candidate for the first ever discovered exomoon. Scientists studying data from the Kepler Space Telescope noticed unusual transit timing variations in the planet Kepler-1625b, a massive gas giant orbiting a sun-like star about 8,000 light-years away. The data suggested that there might be a Neptune-sized moon orbiting the planet, which was an unexpected find because such a large moon does not exist in our own solar system. The evidence for Kepler-1625b I was intriguing but not conclusive. Follow-up observations with the Hubble Space Telescope added to the mystery, showing additional anomalies that could indicate the presence of a moon. However, the data was not strong enough to be definitive. The scientific community remains divided on whether this object is truly an exomoon, or if the signals could be explained by other factors, such as instrumental noise or an unseen second planet in the system. Despite the uncertainty, the search for exomoons has gained momentum. Future telescopes, such as the James Webb Space Telescope, JWST, and the upcoming Habitable Worlds Observatory, are expected to provide more precise data that could finally confirm the existence of exomoons. These telescopes will have the ability to study exoplanetary atmospheres in unprecedented detail, potentially detecting atmospheric signatures that hint at moons orbiting them. If we do confirm an exomoon, the next question will be, what is it like? Could it have an atmosphere? Could it have liquid water? Could it even support life? In our solar system, we already see incredible diversity among moons, some with thick atmospheres, like Titan, and others with subsurface oceans, like Europa and Enceladus. If exomoons follow a similar pattern, we might find worlds that challenge everything we thought we knew about habitability. One particularly exciting possibility is that some exomoons might be more hospitable to life than their host planets. Imagine a giant gas planet orbiting in the habitable zone of its star. While the planet itself might be uninhabitable due to extreme atmospheric conditions, its moons could have stable surfaces, thick atmospheres, and the right conditions for life. This means that exomoons could significantly expand the number of places where we might find alien life. There is also the question of what kinds of exomoons exist. In our solar system, we see rocky moons, icy moons, and even captured asteroids that have become moons. If we find an exomoon that appears to be a captured object, it could provide insights into the chaotic nature of planetary formation. Some exomoons might even have rings or their own tiny moonlets, creating systems within systems that could be more complex than anything we've seen before. Beyond the scientific implications, the discovery of an exomoon would be a moment of profound significance for humanity. It would remind us that our solar system is not unique, that the rules of physics and planetary formation apply everywhere in the universe, and that we are just beginning to scratch the surface of what's out there. As technology advances, our ability to detect and study exomoons will only improve. The search is no longer just a theoretical pursuit, it's an active and ongoing effort that could yield groundbreaking discoveries at any moment. We are standing at the edge of a new frontier, one that could redefine our understanding of the universe and our place in it. The first confirmed exomoon is out there, waiting to be found. And when we finally see it, it won't just be a distant object orbiting a faraway planet. It will be a glimpse into a world that has been hidden from us for millennia, a world that could challenge our perceptions, expand our possibilities, and bring us one step closer to answering the greatest question of all: are we alone in the universe? The idea that exomoons could be more common than we ever imagined is something that keeps astronomers awake at night. If even one exomoon can be confirmed, then it opens up the possibility that there are billions, maybe even trillions, of them scattered throughout the galaxy. Each of these moons could be a potential world of its own, with its own climate, geography, and possibly even its own unique conditions for life. But the search for these elusive moons is not just about numbers. It's about understanding how planetary systems form and evolve over time. One of the biggest questions surrounding exomoons is how they form. In our solar system, moons form in a few different ways. Some, like our own moon, are thought to have formed from giant impacts that ejected debris into orbit, which then coalesced into a satellite. Others, like Jupiter's Galilean moons, likely formed in a miniature version of the process that created the planets, by gradually accumulating material from the surrounding disk of gas and dust. And some moons, like Neptune's Triton, are believed to have been captured from elsewhere, possibly from the Kuiper Belt or even interstellar space. If exomoons exist in other planetary systems, they might follow similar patterns, or they might form in ways we've never seen before. For instance, some scientists have speculated that certain gas giants might have once been stars that failed to ignite. If these failed stars had smaller objects orbiting them before they were captured by a larger star's gravity, then their moons could be much older than the planets themselves. This means that exomoons could hold clues to events that happened billions of years before their current planetary system even formed. The nature of these moons is also a subject of great debate. Could they have atmospheres? Could they have their own magnetic fields? Could they even have liquid water? On Earth, liquid water is essential for life, and we already know of moons in our solar system, like Europa and Enceladus, that are believed to have vast underground oceans. If similar conditions exist on exomoons, then the potential for finding extraterrestrial life increases dramatically. One of the most fascinating possibilities is that some exomoons might have conditions even more suitable for life than their parent planets. A planet in the habitable zone might have an exomoon that retains heat better due to tidal forces, has a thick atmosphere to regulate its climate, or orbits in such a way that it avoids extreme seasonal variations. In these cases, the moon, rather than the planet, could be the best candidate for supporting life. But finding an exomoon is one thing, proving that it has the right conditions for life is another. Future telescopes, like the James Webb Space Telescope and its successors, might be able to analyze the atmospheres of exomoons, looking for chemical signatures that could indicate habitability. If we find an exomoon with an atmosphere rich in oxygen, methane, or other gases associated with biological processes, it would be a groundbreaking discovery. The implications of such a find would be staggering. For centuries, humanity has wondered whether we are alone in the universe. If we find even the faintest sign of life on an exomoon, it would mean that life is not unique to Earth. It is a natural consequence of the right conditions coming together. It would suggest that life could exist in countless places across the cosmos, hidden on the moons of distant planets that we are only just beginning to detect. Beyond the search for life, the study of exomoons could also change our understanding of planetary formation. If we find exomoons that orbit rogue planets that have been ejected from their original star systems, then we might learn more about how planets migrate through space. Some exomoons could be relics of ancient planetary systems, carrying evidence of events that happened billions of years ago, before our own solar system even existed. The possibility of habitable exomoons also raises intriguing questions about the future of human exploration. If we ever develop the technology to travel between star systems, exomoons might be some of the first destinations we visit. Unlike massive gas giants, which have crushing atmospheres and extreme conditions, moons could provide stable surfaces, moderate climates, and even resources that future astronauts could use to survive. Some scientists have even speculated about the possibility of superhabitable exomoons, moons that have conditions even better than those on Earth. If a moon is large enough to have strong gravity, but not so large that it becomes a gas giant, it could retain a thick atmosphere, maintain liquid water, and have stable temperatures. Such a moon could be one of the most ideal places for life in the universe. The more we search, the more we realize just how much we don't know. Every time astronomers make a new discovery, it seems to raise more questions than answers. Are exomoons common, or are they rare? Are they more like the moons in our solar system, or do they follow completely different rules? Could some of them be habitable, or even home to alien life right now? The search for exomoons is still in its early days, but it is already reshaping the way we think about the universe. It reminds us that the cosmos is full of mysteries, waiting to be uncovered. And perhaps, one day in the not-so-distant future, we will finally get the confirmation we've been waiting for, the discovery of a true exomoon, orbiting a distant planet, revealing a whole new world that was hidden in the shadows of space. The idea that exomoons could be home to life is one of the most exciting possibilities in modern astronomy. If we find an exomoon with an atmosphere, the next step would be to analyze its composition. The presence of oxygen, methane, carbon dioxide, or even complex organic molecules could be a sign that biological processes are occurring. But detecting these gases is not easy. Even for exoplanets, atmospheric analysis is still in its infancy, requiring advanced techniques like transmission spectroscopy, where a planet's atmosphere is studied as it passes in front of its star. If an exomoon is small, its signal would be even fainter, making the challenge exponentially harder. Still, scientists remain optimistic. The James Webb Space Telescope, launched with the ability to analyze exoplanet atmospheres in detail, has given hope that exomoons may one day be studied in a similar way. But as promising as Webb is, it may not be enough. Future space telescopes will likely need to be even more powerful, possibly using techniques like direct imaging, where a planet and its potential moon are observed without relying on transits. This could involve giant space-based telescopes equipped with advanced coronagraphs to block out starlight and reveal hidden details of planetary systems. One fascinating question about exomoons is whether they could support liquid water even outside a star's habitable zone. In our solar system, we see evidence of this on moons like Europa, Enceladus, and even Titan, where subsurface oceans exist beneath layers of ice. The key factor here is tidal heating. When a moon orbits a massive planet, the gravitational pull from the planet stretches and compresses the moon, generating internal heat. This process could allow some exomoons to remain warm enough for liquid water even if they orbit planets that are far from their parent stars. If tidal heating is strong enough, it could make exomoons habitable even in places where their host planets are frozen and lifeless. This expands the range of places where life could potentially exist. For example, A gas giant orbiting a red dwarf star might be in a region that is too cold for life, but its moon could still have a warm, liquid ocean under its surface due to tidal forces. This means that when searching for exomoons, astronomers might need to look beyond just the habitable zone of a star and consider the internal heating effects caused by gravitational interactions. Another question is how common exomoons might be. If most large exoplanets have moons, then the number of potential worlds in the universe increases dramatically. Instead of just counting planets in habitable zones, astronomers would have to consider their moons as well, essentially doubling or tripling the number of places where life might exist. This would change our perspective on the search for extraterrestrial life. But could an exomoon ever develop intelligent life? It's an intriguing possibility. If an exomoon had a stable climate, liquid water, and a strong atmosphere, it could be a perfect place for life to evolve. One advantage an exomoon might have over a planet is protection. If the moon orbits a massive gas giant, the planet's magnetic field could shield it from harmful cosmic radiation, creating a safer environment for life. Additionally, if the planet has a thick atmosphere, it could absorb some of the impacts from asteroids or comets, reducing the risk of catastrophic extinction events. If intelligent life did evolve on an exomoon, it might experience the universe in a completely different way than we do. Imagine a civilization that grew up on a moon orbiting a gas giant. Instead of seeing a single sun in the sky, they would see their massive planet dominating the heavens, possibly with other moons visible in the distance. Their night sky might be illuminated by the reflected light of the gas giant, creating a world with permanent twilight. If their moon was tidally locked, they might have one hemisphere where the planet is always visible, while the other side experiences a more normal day-night cycle. Such a civilization might develop different concepts of time, and even different approaches to science. Would they wonder about the other moons in their sky, dreaming of exploring them before ever thinking of the stars beyond? If they became an advanced spacefaring species, their first journeys would likely be to their planetary neighbor, rather than to distant exoplanets. Of course, all of this is speculation, but it shows just how important the search for exomoons could be. If we find one, it could reshape our understanding of habitability, planetary formation, and even the potential for alien life. But the hunt for exomoons is not just about looking for life, it's also about solving fundamental mysteries of how planetary systems work. Scientists still don't fully understand why some planets in our own solar system have large moons while others do not. Mars, for example, only has 2 tiny captured asteroids as moons, while Jupiter and Saturn have dozens of major moons. If we can study exomoons around distant planets, we might finally get answers about why some planets end up with large, stable satellites while others do not. The search for the first exomoon is also a technological challenge. Even though telescopes are improving, detecting something as small as a moon around a distant exoplanet is pushing the limits of what is currently possible. Scientists have proposed several methods to detect exomoons, but each comes with its own difficulties. One approach is to look at the way an exoplanet wobbles. If a planet has a large moon, the gravitational pull of the moon will cause the planet to shift slightly as it orbits its star. This creates tiny variations in the timing of the planet's transits, when it passes in front of its star from our perspective. By studying these variations, astronomers can look for evidence of an unseen moon. Another method is direct imaging, though it is much harder. Directly spotting a moon next to an exoplanet would require an incredibly powerful telescope with high resolution, and even then, the brightness of the planet might overwhelm the faint light from the moon. Scientists have also considered using radio telescopes to detect magnetic fields around exomoons. If an exomoon has a strong magnetic field, it could interact with the surrounding space environment in a way that produces detectable radio signals. This method is still theoretical, but it could provide a new way to search for exomoons without relying on light-based observations. Despite all these challenges, astronomers are making progress. Several exomoon candidates have been proposed, though none have been confirmed beyond doubt. The most famous of these is Kepler-1625b I, a possible exomoon orbiting a gas giant about 8,000 light-years away. Initial observations suggested that the planet's transit was slightly irregular, hinting at the presence of a moon. However, follow-up observations were inconclusive, and astronomers are still debating whether it was a real detection or just noise in the data. The search for the first exomoon continues, and with each new discovery, we get closer to answering some of the biggest questions about the universe. Are moons common in other planetary systems? Could they be habitable? And if they are, could they even be home to life? The universe is vast, and its mysteries are endless. The discovery of an exomoon would be a landmark achievement in astronomy, but it would also be just the beginning. Once we find one, we will want to find more. We will want to study them, compare them, and understand what makes them unique. And if we ever find one that has the right conditions for life, it could be one of the most important discoveries in human history. The search is still in its early days, but one thing is certain: the hunt for exomoons is one of the most exciting frontiers in space exploration. The first confirmed exomoon may still be waiting out there, hidden in the shadows of a distant planet, just waiting for us to find it. And when we do, it could change everything we know about the universe and our place in it. The discovery of the first exomoon would be a breakthrough not just for astronomy, but for our understanding of planetary systems as a whole. It would confirm that moons are not unique to our solar system but are likely a fundamental part of planetary formation throughout the universe. But beyond that, it would open up an entirely new category of celestial bodies to explore. Just as exoplanets have reshaped our knowledge of planetary diversity, exomoons could do the same, revealing new types of worlds that we never imagined. One of the biggest questions surrounding exomoons is how they form. In our solar system, moons originate in different ways. Some, like Earth's moon, are thought to have formed from giant impacts, where a massive collision threw debris into orbit that eventually coalesced into a moon. Others, like the moons of Jupiter and Saturn, are believed to have formed from the same disk of gas and dust that created their parent planets. Then there are moons like Neptune's Triton, which was likely a captured object from the Kuiper belt. Understanding how exomoons form could give us new insights into how planets evolve, and why some planets end up with moons while others do not. If we confirm an exomoon, one of the first things scientists will want to study is its composition. Is it rocky like our moon? Icy like Europa? Does it have an atmosphere? The answers to these questions will help us understand how similar or different exomoons are compared to the moons we see in our own solar system. If we find an exomoon with a thick atmosphere, it could be an incredible target for future research, as it may have the potential to support life. There's also the question of stability. Many of the exoplanets we've discovered are in extreme environments, some orbiting very close to their stars, others locked in chaotic gravitational interactions with multiple planets. If an exomoon exists in such a system, how does it remain stable? Would it get torn apart by tidal forces, or could it persist for billions of years? Answering these questions could help us understand the long-term evolution of planetary systems and whether exomoons are common or rare. One particularly intriguing idea is the possibility of habitable exomoons around gas giants in the habitable zones of their stars. If a gas giant orbits in the right region where liquid water can exist, its moons might have the right conditions for life. In fact, some scientists believe exomoons could be even better candidates for life than exoplanets. For one, exomoons could benefit from multiple sources of energy. A planet like Earth primarily relies on sunlight, but a habitable exomoon could receive energy not just from its star but also from the radiation and tidal forces of its parent planet. This could keep it warm even if it is farther from its star than a typical habitable exoplanet. Another advantage is protection. A large planet with a strong magnetic field could shield its moons from harmful radiation, creating a stable environment for life to develop. Additionally, the gravitational pull of the planet could help stabilize the moon's climate, reducing the risk of extreme temperature swings that could threaten habitability. However, there are also challenges. Exomoons may be exposed to intense radiation from their parent planets, especially if they orbit close to a giant planet with a strong magnetic field. Jupiter's moon Io, for example, is bombarded by radiation from Jupiter's magnetosphere, making its surface extremely hostile. If an exomoon is too close to its planet, it may be exposed to similar dangers, reducing its chances of supporting life. Another factor to consider is the effect of tidal forces. If an exomoon experiences strong tidal heating, it could generate enough internal heat to maintain a subsurface ocean, similar to Europa or Enceladus. However, if the heating is too extreme, it could lead to excessive volcanic activity, or even prevent stable conditions for life. Finding the right balance is crucial in determining whether an exomoon could truly be habitable. Despite these challenges, the search for exomoons is advancing rapidly. New telescopes and observation techniques are being developed, increasing the chances of detecting the first confirmed exomoon. The next generation of space telescopes, such as the Habitable Worlds Observatory and other planned missions, could provide the capabilities needed to study exomoons in detail. One promising approach is to look for exomoons using the method of transit timing variations, TTV, and transit duration variations, TDV. When an exoplanet passes in front of its star, its transit follows a predictable pattern. However, if an exomoon is present, its gravitational influence can cause the transit to shift slightly in timing or duration. By carefully analyzing these small deviations, astronomers can infer the presence of a moon. Another method involves looking for exomoons using radio signals. Some researchers suggest that if an exomoon has a magnetic field, it could interact with the surrounding space environment in a way that produces detectable radio emissions. If we can develop instruments sensitive enough to pick up these signals, we may be able to identify exomoons even if they are too small to detect using traditional methods. The most exciting prospect is direct imaging. While current telescopes struggle to directly observe exoplanets, future instruments may be powerful enough to capture images of exoplanets and their moons. If we can directly image an exomoon, we would be able to analyze its atmosphere, surface composition, and even potential weather patterns, providing a wealth of information about these mysterious worlds. But the search for exomoons is not just about finding another celestial body, it's about rewriting what we know about the universe. If we confirm that exomoons exist in large numbers, it would mean that the number of potentially habitable worlds in the cosmos is far greater than we ever imagined. Instead of just looking for exoplanets in habitable zones, we would have to consider their moons as well, effectively multiplying the number of worlds where life could emerge. It would also raise profound questions about the nature of life itself. Could life on an exomoon evolve differently than life on a planet? Would an intelligent species on an exomoon develop a different understanding of the cosmos, shaped by the presence of a massive planet dominating their sky? These are questions that we can only begin to speculate about, but they add to the excitement of the search. The first confirmed exomoon may already be in our data, waiting to be discovered. Or it may require the next generation of telescopes to finally be found. Either way, the search continues, driven by the curiosity and determination of scientists around the world. And when that discovery finally happens, it will mark the beginning of an entirely new chapter in our understanding of the universe. The implications of finding the first confirmed exomoon extend far beyond simply adding another celestial body to our growing catalog of discoveries. It would change how we understand planetary systems, challenge our theories of moon formation, and expand the search for habitable worlds in ways we never imagined. But despite the promise, the search for exomoons remains one of the most challenging endeavors in modern astronomy. Unlike exoplanets, which can be large enough to block a measurable fraction of their star's light during transits, exomoons are significantly smaller and harder to detect. Even the largest moons in our own solar system, like Ganymede or Titan, would be incredibly difficult to spot if they were orbiting a planet outside our solar system. One of the biggest challenges is distinguishing the signal of an exomoon from the noise of other astronomical phenomena. The variations in transit timing and transit duration that scientists look for could also be caused by multiple planets interacting with each other. Additionally, stellar activity, such as sunspots and flares, can create fluctuations in light that mimic the effects of an exomoon. This makes it difficult to determine with certainty whether an observed irregularity is truly the sign of a moon or just a misinterpretation of unrelated data. Another major challenge is the size of exomoons relative to their parent planets. Even the largest moons in our solar system are only a fraction of the size of their planets. For example, Earth's moon is about 1/4 the diameter of Earth, while Titan is about 1/23 the diameter of Saturn. If exomoons follow a similar pattern, their size compared to their planets may be too small to produce a detectable transit effect. This means that only the largest exomoons, ones much bigger than any seen in our solar system, would be detectable with current methods. If such moons exist, they could represent an entirely new class of celestial objects, possibly even rivaling small planets in size. The idea of giant exomoons, sometimes called supermoons, raises fascinating questions about how they form. In our solar system, moons tend to be much smaller than their parent planets. But what if exomoons in other systems can grow to be as large as Mars, or even Earth? Could they have their own thick atmospheres? Could they have weather patterns, oceans, and possibly life? The possibility of habitable exomoons has led some scientists to speculate that they might even be more common than habitable exoplanets. If giant gas planets with habitable exomoons exist, they could be some of the best places to look for extraterrestrial life. One of the most interesting aspects of exomoons is their potential to exist in a variety of environments that we haven't seen in our solar system. For example, some theorists have proposed that exomoons could exist in binary star systems, orbiting planets that in turn orbit two stars. This would create a world where the sky is dominated by two suns, much like the famous twin sunsets seen on Tatooine in Star Wars. The dynamics of such a system would be complex, but if an exomoon could remain stable in such an environment, it might experience unique climate patterns due to the changing positions of its two parent stars. There's also the possibility of rogue exomoons, moons that have been ejected from their planetary systems and now drift through space alone. Just as some planets are thought to be rogue planets that have been flung from their solar systems, the same could theoretically happen to moons. If a large planet is involved in a gravitational interaction with another massive object, its moon could be pulled away and sent flying through interstellar space. These rogue exomoons, if they exist, would be nearly impossible to detect, but they could be fascinating in their own right. If they retained a thick atmosphere and internal heat, they might even be able to support life despite being completely detached from any star or planet. One of the most exciting aspects of the exomoon search is how it intersects with the search for alien life. If exomoons exist around gas giants and habitable zones, they might be among the best places to look for biosignatures, chemical signs of life. Scientists could search for atmospheric signatures like oxygen, methane, and water vapor, which might indicate the presence of biological processes. Future telescopes, such as the Habitable Worlds Observatory and other planned missions, could help scientists analyze the atmospheres of these moons in greater detail. If an exomoon's atmosphere shows signs of active chemistry similar to Earth's, it could be a strong indicator that life exists beyond our planet. The discovery of the first exomoon would also have major implications for planetary system formation. If exomoons are common, it would suggest that the processes that create moons in our solar system are universal, occurring in planetary systems across the galaxy. However, if exomoons are rare, it might mean that our own solar system is somewhat unique in the way its moons formed. Either way, the first confirmed exomoon would provide a valuable data point in understanding how planets and moons evolve over time. Another intriguing possibility is that exomoons could host subsurface oceans, much like Europa and Enceladus in our solar system. These moons, despite being covered in ice, have vast oceans beneath their surfaces due to tidal heating from their parent planets. If similar exomoons exist around exoplanets, they might also have subsurface oceans, potentially harboring life in environments completely cut off from sunlight. This raises the exciting possibility that life could exist deep beneath the icy crust of an exomoon, sustained by geothermal energy rather than stellar radiation. The search for exomoons is still in its early stages, but every new piece of data brings us closer to a groundbreaking discovery. With each improvement in telescope technology, our ability to detect smaller and more distant objects increases. The James Webb Space Telescope and upcoming space missions could provide the key to finally identifying an exomoon beyond our solar system. Whether the first confirmed exomoon is a giant, supermoon, or a smaller, Earth-like world, its discovery will undoubtedly change the way we view our place in the universe. For now, astronomers continue to scan the skies, analyzing transit data, refining their models, and searching for that unmistakable signal that could reveal the presence of an exomoon. And when that moment comes, when we finally confirm that moons exist around other planets, it will be one of the most significant discoveries in the history of space exploration. It will mean that the universe is filled with not just countless planets, but also countless moons, each with their own unique characteristics, histories, and perhaps even their own versions of life. The journey to finding the first exomoon is one of patience, precision, and relentless curiosity. It is a story of astronomers pushing the boundaries of what is possible, developing new techniques, and exploring the unknown. And while we have yet to confirm the existence of an exomoon, one thing is certain: the discovery is out there, waiting to be made. It may take years or even decades, but when it happens, it will redefine what we know about planetary systems and open up a whole new frontier in the search for life beyond Earth. The discovery of the first exomoon is not just a scientific milestone, it would be a fundamental shift in our understanding of planetary systems. While exoplanets have dominated space exploration headlines for the last few decades, moons could be just as important in shaping the nature of alien worlds. If exomoons are common, they could vastly outnumber planets in the universe, making them one of the most significant types of celestial objects yet to be fully explored. Imagine a galaxy where every gas giant has a system of moons, some resembling Europa with icy shells covering vast oceans, others like Titan with thick atmospheres, or even Earth-like moons orbiting massive planets in habitable zones. The variety could be staggering, and each one could be a potential home for life. One of the biggest questions scientists have is whether exomoons follow the same formation processes as the moons in our solar system. Here, we see three main ways moons form. Some, like our moon, are thought to have formed from giant impacts, where a collision between a planet and another body creates debris that eventually coalesces into a moon. Others, like the moons of Jupiter and Saturn, likely formed from the same protoplanetary disk that gave birth to their parent planets. And then there are captured moons, like Neptune's Triton, which may have originally been a dwarf planet that was pulled into orbit by Neptune's gravity. If exomoons exist, which of these formation processes dominates? Do most exomoons form through impact events, or do they emerge naturally alongside their planets? Understanding exomoon formation could help us piece together how planetary systems evolve over time. If exomoons are mostly captured objects, it would suggest that planetary systems are highly dynamic, with bodies frequently changing orbits and being ejected or captured. If they form alongside their planets, it might mean that large planets with big moon systems are common throughout the galaxy, potentially mirroring what we see with Jupiter and Saturn. But if exomoons mostly form from giant impacts, that would imply that planetary collisions are a frequent occurrence in the universe. Any of these possibilities would reshape our understanding of how planets and moons interact on a cosmic scale. Another critical aspect of exomoons is their potential for habitability. While exoplanets in the habitable zone of their stars have been the primary focus of the search for extraterrestrial life, exomoons could offer even more possibilities. A large moon orbiting a gas giant in the habitable zone could have conditions similar to Earth, with liquid water, a stable atmosphere, and even seasons caused by its planet's gravitational influence. In some cases, exomoons could even be better candidates for life than planets. If a planet is too close to its star and experiences extreme radiation or tidal locking, where one side always faces the star, an exomoon orbiting a farther out gas giant might have a more stable environment for life to thrive. The search for life on exomoons also raises the fascinating possibility of worlds with multiple sources of energy. In our solar system, we see examples of moons that generate heat through tidal forces, such as Europa and Enceladus, where gravitational interactions with Jupiter and Saturn create internal heating. This means that even if an exomoon is located outside the traditional habitable zone, it could still have liquid water beneath its surface due to geothermal activity. If similar mechanisms exist on exomoons orbiting exoplanets, it would dramatically expand the potential locations where life could exist. One of the more speculative but exciting ideas is the possibility of intelligent life evolving on an exomoon rather than a planet. If an exomoon were large enough and had Earth-like conditions, it could theoretically support advanced civilizations. However, living on an exomoon would come with unique challenges. The gravitational pull of a massive planet could create extreme tides, leading to dramatic environmental changes. The exomoon would also experience frequent eclipses, as its planet would periodically block the light from the star, potentially affecting climate and energy availability. These conditions could shape the evolution of life in ways we can only begin to imagine. Looking forward, the next generation of telescopes will be crucial in advancing the search for exomoons. The James Webb Space Telescope, JWST, has already started providing some of the most detailed observations of exoplanets ever recorded, and as scientists refine their techniques, it may eventually be capable of detecting exomoons as well. Future missions like the Habitable Worlds Observatory will be specifically designed to search for signs of habitability beyond our solar system, and exomoons will likely be a key target of study. But even as technology advances, the hunt for exomoons will remain one of the most challenging tasks in astronomy. The signals scientists are looking for are incredibly subtle, and distinguishing an exomoon from other possible explanations requires extreme precision. It may take years or even decades before a discovery is confirmed beyond doubt. However, history has shown that patience in astronomy is often rewarded. Not long ago, exoplanets themselves were purely theoretical, and now thousands have been confirmed. The same could happen with exomoons, and when the first definitive detection is made, it will mark the beginning of a whole new era in space exploration. Imagine the moment when astronomers finally detect an exomoon with certainty. The data would be analyzed, models would be refined, and eventually, the world would hear the announcement: we have found the first confirmed moon orbiting a planet beyond our solar system. The implications would be profound, not just for scientists but for anyone who has ever looked up at the night sky and wondered what else is out there. That first discovery would be just the beginning, paving the way for the study of other exomoons, each with their own unique characteristics. Some might be barren and rocky, while others might have thick atmospheres or even vast oceans. Each new discovery would bring us closer to answering some of the biggest questions in science: how planetary systems form, how moons evolve, and whether life exists beyond Earth. The search for the first exomoon is one of the most exciting frontiers in modern astronomy. It's a journey that requires patience, innovation, and an unshakable curiosity about the universe. And while the first confirmed exomoon has yet to be found, the search is well underway. One day, maybe sooner than we think, we will look at a distant exoplanet and know with certainty that a moon is orbiting it. And with that discovery, a new chapter in our understanding of the cosmos will begin. The search for exomoons is about more than just adding another category to our cosmic catalog. It's about unlocking a deeper understanding of how planetary systems work, how celestial bodies interact, and ultimately, how life might emerge beyond Earth. Every time we push the boundaries of what we can detect, we get closer to uncovering secrets that have been hidden for billions of years. If we confirm the existence of exomoons, we'll be rewriting the rules of planetary formation and habitability. One of the biggest challenges in detecting exomoons is that they're much smaller than their parent planets. When looking for exoplanets, astronomers often use the transit method, where they measure tiny dips in a star's brightness as a planet passes in front of it. But if a planet has a moon, that moon would cause even smaller, more irregular dips, making it incredibly difficult to distinguish from random noise. The signal of an exomoon can easily be lost in the complexity of a planet's transit. Scientists have had to develop advanced statistical models to identify potential exomoons among the thousands of exoplanet observations already collected. One of the most promising candidates for an exomoon was found orbiting the exoplanet Kepler-1625b I. This potential exomoon, called Kepler-1625b I, appeared to create anomalies in the planet's transit signal, suggesting that something was orbiting the planet itself. Follow-up observations with the Hubble Space Telescope provided additional evidence, but it wasn't definitive. The problem is that even the best telescopes struggle to resolve such fine details, and many astronomers remain cautious about confirming the existence of this exomoon. If it is real, it could be a Neptune-sized moon orbiting a Jupiter-sized planet, a configuration unlike anything in our solar system. But until more data is collected, its status remains uncertain. The search for exomoons also raises fascinating questions about the stability of these systems. In our solar system, moons orbiting massive planets remain stable due to well-defined gravitational relationships. But in an exoplanetary system, where the planet may be much closer to its star or in a highly eccentric orbit, the gravitational forces acting on a moon could be far more chaotic. Some exomoons might not last long before being ripped apart by tidal forces or ejected from their planetary systems entirely. Others might have highly elliptical orbits, swinging back and forth between their planets and deep space in ways that would create bizarre and unpredictable environments. Another possibility is that some exomoons could be habitable even if their parent planets are not. A gas giant orbiting close to its star might be an inhospitable world, with extreme temperatures and radiation levels. But if it has a large moon with an atmosphere and magnetic field, that moon could be shielded from the worst of the star's radiation. This means that habitable moons could exist in places where habitable planets never could. This idea is particularly exciting because it suggests that we might need to rethink the way we search for life. Instead of only focusing on exoplanets and habitable zones, we may also need to examine the moons of those planets for signs of habitability. Some researchers have even speculated that exomoons could be the best place to look for intelligent extraterrestrial civilizations. A highly advanced civilization might prefer to settle on a stable exomoon rather than a planet, especially if the moon has access to energy sources like tidal heating or a thick atmosphere to support agriculture and industry. If exomoons are abundant throughout the universe, it raises the possibility that the most advanced civilizations we could detect might not be living on planets at all. While the search for exomoons continues, astronomers are also considering how we might one day explore them directly. Right now, exoplanets are too far away for spacecraft to visit, but future breakthroughs in propulsion technology could make interstellar travel a reality. If humanity ever develops the capability to send probes beyond our solar system, exomoons will be among the most intriguing targets. A probe arriving in a distant star system might find not just a planet, but an entire system of moons, each with unique landscapes, atmospheres, and potential for life. Some might be barren and cratered like our moon, while others could have vast oceans, towering mountains, or dense jungles. The possibilities are endless. For now, the best we can do is refine our detection methods and continue scanning the cosmos for hints of these elusive worlds. Every improvement in telescope technology brings us closer to confirming the first exomoon, and once we find one, the floodgates will open. Just as the discovery of the first exoplanets led to thousands more being found, the first confirmed exomoon could pave the way for a new era of exploration. In the near future, we may look up at the night sky and know that, among the countless stars, there are moons orbiting planets in distant solar systems, moons that might be home to alien life. The implications of discovering exomoons stretch far beyond simply adding new celestial bodies to our catalog of known objects in the universe. It forces us to rethink fundamental questions about how planets and moons form, how they evolve, and what kinds of environments might be suitable for life. In many ways, the study of exomoons is an extension of the search for habitable worlds, but with even more complexity. One of the biggest mysteries surrounding exomoons is their potential to host life. While planets are often the primary focus of astrobiology, moons in our own solar system have demonstrated that they can be just as, if not more, interesting when it comes to habitability. Moons like Europa and Enceladus contain vast oceans beneath their icy crusts, with evidence of geothermal activity that could support life. If moons like these exist beyond our solar system, it raises the exciting possibility that some exomoons could harbor life even in systems where the planets themselves are inhospitable. But how do these moons form in the first place? There are several theories about how moons come into existence. Some form from the leftover material around a planet, much like how planets form around stars. Others are captured objects, asteroids, or even former planets that were pulled into orbit by a larger body's gravity. Some are the result of massive collisions, where a planet's violent impact with another object creates a debris field that eventually coalesces into a moon. In our own solar system, we see all three of these formation processes at work. But outside our solar system, where conditions can be wildly different, could there be entirely new ways for moons to form? Could some exomoons have origins we've never even considered? Another question that has astronomers scratching their heads is, just how common are exomoons? In our solar system, most large planets have multiple moons. Jupiter alone has over 90 known moons, with some still being discovered. If exoplanetary systems are anything like our own, then many of the giant exoplanets we've found should also have their own moons. But so far, we haven't been able to confirm even one. Why? Is it just that our technology isn't advanced enough yet, or could it be that exomoons are rarer than we think? Some scientists suspect that the conditions required for a stable exomoon orbit might be harder to achieve than we realize. In a multi-planet system, gravitational forces from nearby planets could disrupt moon formation or pull moons away from their parent planets. Similarly, if a planet orbits too close to its star, tidal forces might strip it of any moons before they have a chance to stabilize. It's possible that many exomoons exist only temporarily before being ejected into interstellar space. Even if exomoons are common, detecting them is an entirely different challenge. Unlike planets, which can cause clear and consistent dips in their star's brightness during a transit, moons create much more subtle effects. Their orbits can be irregular, their signals weak, and their presence easily mistaken for noise in the data. This is why astronomers have to use extremely precise statistical techniques to tease out the signatures of potential exomoons from the thousands of exoplanet transits recorded by telescopes like Kepler and TESS. The search for the first confirmed exomoon is also a race against time. Many of the best candidate systems for exomoons are already at the limits of what our current telescopes can observe. As new space telescopes like the James Webb Space Telescope, JWST, and future missions come online, we may finally have the resolution needed to detect these elusive worlds. Some researchers are even proposing dedicated exomoon hunting missions that would focus specifically on finding and studying moons in distant solar systems. One of the most fascinating possibilities is that some exomoons might be even more Earth-like than the exoplanets they orbit. Consider a scenario where a large, rocky exomoon orbits a gas giant in the habitable zone of its star. The gas giant itself might be completely inhospitable, with crushing atmospheric pressure and no solid surface, but its moon could have a stable climate, liquid water, and even an atmosphere rich in oxygen. It's entirely possible that some exomoons could be the true gems of their star systems, hidden oases of life in an otherwise hostile environment. Some scientists have even speculated that exomoons could be better places to search for extraterrestrial civilizations than exoplanets themselves. A technologically advanced civilization might prefer to colonize a large, habitable moon orbiting a gas giant because it could provide natural protection against space radiation and other hazards. If these civilizations exist, they might be using energy sources like tidal heating, fusion, or even artificial megastructures to sustain themselves. The idea that moons could be prime real estate for life is further supported by what we see in our own solar system. Europa, one of Jupiter's largest moons, has a global ocean beneath its icy surface, and scientists believe hydrothermal vents on its ocean floor could provide the necessary ingredients for life. Titan, Saturn's largest moon, has lakes of liquid methane and an atmosphere rich in organic compounds. Enceladus, another of Saturn's moons, is actively spewing water and organic material into space from geysers near its south pole. If such conditions exist on moons in our own backyard, it's not unreasonable to think they could be common in other star systems as well. Another exciting development in the search for exomoons is the possibility of directly imaging them. While current methods rely on indirect detection, future telescopes could be powerful enough to actually capture images of exoplanets and their moons. This would be a game-changer, allowing scientists to study their atmospheres, climates, and even surface features. Imagine seeing an actual photo of an Earth-like exomoon orbiting a distant gas giant, an image that could provide the first glimpse of a truly alien world. The search for exomoons is one of the most exciting frontiers in modern astronomy, filled with mystery, challenges, and the potential for groundbreaking discoveries. If we confirm even a single exomoon, it will open up an entirely new chapter in our understanding of the cosmos. It will change the way we think about planetary systems, the conditions for life, and our place in the universe. And perhaps, in the not-too-distant future, we'll look up at the night sky knowing that, somewhere out there, an exomoon is orbiting a distant world, waiting for us to find it. The search for exomoons is not just a scientific curiosity, it's a quest that could fundamentally reshape our understanding of planetary systems, the origins of life, and the very nature of the universe. If exomoons are as common as many astronomers suspect, then the implications are profound. It would mean that our own solar system, with its diverse collection of moons, is not unique but part of a much larger cosmic pattern. It would suggest that moons could be an essential part of planetary evolution, possibly playing a crucial role in shaping the habitability of worlds beyond our own. One of the most fascinating aspects of exomoons is the possibility that they could be more geologically active than their parent planets. We see evidence of this in our solar system, where moons like Io, Europa, and Enceladus exhibit intense volcanic activity, subsurface oceans, and even geysers that spew water and organic material into space. The reason for this activity lies in tidal forces, gravitational interactions between a moon, its host planet, and sometimes other moons in the system. These forces create internal friction, heating up the moon's interior and driving geological activity. If similar tidal forces are at play in exomoon systems, then some of these distant moons could be among the most volcanically active worlds in the universe. Imagine a moon covered in vast lava fields, with constant eruptions reshaping its surface. Or a moon with geysers so powerful they create massive plumes that reach hundreds of kilometers into space. Such worlds would be extreme, but they could also be incredibly dynamic environments that might even support some form of life. Another intriguing possibility is that exomoons could have atmospheres, much like Titan, Saturn's largest moon. Titan is the only moon in our solar system with a thick atmosphere, composed mainly of nitrogen with traces of methane. This atmosphere creates a climate with weather patterns, rain, and even lakes, though instead of water, they are filled with liquid hydrocarbons. If exomoons in other systems have similar atmospheres, they could be among the most Earth-like worlds we have ever discovered. Some might have clouds and precipitation, possibly even water-based weather systems. Others might have exotic chemical compositions that create entirely new forms of climate and meteorology. But exomoons could also face challenges that make their environments vastly different from anything we see on Earth. One major factor is radiation. Many large exoplanets orbit close to their stars, which means that any moons they host could be bombarded by intense stellar radiation. If these planets are gas giants, they might also have strong magnetic fields that generate powerful radiation belts. In our solar system, Jupiter's radiation belts make its inner moons highly inhospitable, with levels of radiation that would be lethal to humans in a matter of hours. If similar conditions exist around exoplanets, then some exomoons might be exposed to extreme radiation, making habitability much more difficult. However, radiation isn't necessarily a deal-breaker. Some moons could have thick atmospheres that protect them from harmful rays. Others might have strong magnetic fields of their own, acting as a shield against their planet's radiation. And some could have subsurface oceans, like Europa, where life could thrive in a protected environment far from the surface. Another question that astronomers are grappling with is whether exomoons could ever be truly independent worlds. In our solar system, all known moons are gravitationally bound to their parent planets, meaning they will never escape their orbits unless some external force disrupts them. But in other systems, it's possible that large moons could eventually break free from their planets and become rogue moons, wandering the galaxy as independent celestial bodies. If such rogue moons exist, there would be a new class of objects entirely separate from planets, asteroids, and traditional moons. They might be difficult to detect, but if we could find one, it would provide valuable insights into how moons evolve over time. Some rogue moons might even retain atmospheres or internal heat for millions of years, creating bizarre, isolated environments floating through interstellar space. The search for exomoons is still in its infancy, but the potential discoveries ahead could be nothing short of revolutionary. With next-generation telescopes coming online, astronomers will soon have better tools to detect these elusive worlds. The James Webb Space Telescope, for example, has the capability to analyze the atmospheres of exoplanets, and it may eventually be able to detect exomoons indirectly by observing their effects on their host planets. Future missions like the proposed LUVOIR, Large Ultraviolet Optical Infrared Surveyor, and HABEX, Habitable Exoplanet Observatory, could provide even more powerful ways to study exomoons. These telescopes could directly image exoplanetary systems, capturing detailed observations of both planets and their potential moons. And as technology continues to advance, we may eventually reach a point where we can not only detect exomoons but also study their climates, compositions, and even potential biosignatures. One of the most exciting aspects of this search is that it's not just about finding moons, it's about understanding the broader picture of how planetary systems evolve. Every discovery brings new questions. Do all gas giants have moons, or are there exceptions? Could some exomoons be more massive than Mercury, or even Mars? Are there entire planetary systems where moons are more common than planets? The search for exomoons is a reminder of how little we still know about the universe. Every time we think we understand the rules of planetary formation, we discover something that challenges our assumptions. Exomoons are the next great mystery waiting to be unraveled, and when we finally confirm their existence, it will be one of the most significant breakthroughs in modern astronomy. And who knows? Perhaps the first confirmed exomoon will be orbiting a planet in the habitable zone, a place where liquid water could exist, where complex chemistry could unfold, and where the conditions for life might just be waiting for us to discover them. The possibility of habitable exomoons is one of the most exciting prospects in modern astronomy. While planets in the habitable zone of their stars have been the main focus of exoplanet research, exomoons offer a completely new dimension to the search for life beyond Earth. If a giant exoplanet orbits in the habitable zone, then any moons it hosts could also be within the same region, potentially making them prime candidates for habitability. Some of these moons might even have conditions that are more favorable for life than their parent planets. One major advantage exomoons might have is the potential for internal heating. Many moons in our solar system, such as Europa, Enceladus, and Io, experience tidal heating due to the gravitational forces exerted by their planets. This heating can drive volcanic activity, create subsurface oceans, and generate the kinds of chemical interactions that are crucial for life. If exomoons in other systems experience similar forces, they could maintain liquid water even if their surfaces are frozen, much like Europa's hidden ocean beneath its icy crust. Another fascinating possibility is that some exomoons could have their own thick atmospheres, allowing for weather, cloud formation, and even complex climate cycles. In our solar system, Titan is a perfect example of how a moon can have an active atmosphere, complete with lakes, rivers, and rain. While Titan's surface is too cold for liquid water, an exomoon in the habitable zone of an exoplanet could have the right conditions for liquid water-based weather systems. This means that instead of just looking at exoplanets for signs of habitability, scientists might need to rethink their search strategies and consider the possibility that some of the best places to find life could actually be moons rather than planets. But there are challenges to consider. One of the biggest is the stability of exomoons in their orbits. In our solar system, large moons tend to orbit relatively close to their planets. If an exoplanet is too close to its star, then tidal forces from the star could disrupt the orbits of any moons, either pulling them away or causing them to spiral into their host planets over time. This means that for an exomoon to remain stable in a habitable zone, it would need to be in a system where the conditions allow it to maintain a long-term orbit. There's also the question of radiation. If an exomoon orbits a giant planet with a strong magnetic field, it could be subjected to intense levels of radiation, much like how Jupiter bombards its moon Europa with high-energy particles. This could be harmful to life unless the exomoon has a strong atmosphere or magnetic field of its own to provide protection. Scientists are still trying to determine whether such conditions could exist in other planetary systems, and this remains one of the key factors in assessing the habitability of exomoons. Despite these challenges, the search for exomoons is only getting started, and new technological advancements are making it more likely that we will detect them in the near future. The James Webb Space Telescope, for example, has the capability to detect subtle variations in the light curves of exoplanets, which could indicate the presence of moons. Future telescopes, such as the proposed LUVOIR and HABEX missions, could provide even more detailed observations, allowing us to directly image exoplanetary systems and possibly even detect the atmospheric signatures of exomoons. One of the most intriguing possibilities is that some exomoons could be more Earth-like than many of the exoplanets we've discovered so far. Many known exoplanets are either gas giants or super-Earths with thick atmospheres that might not be ideal for life as we know it. But if these planets have moons, those moons could be rocky worlds with thin atmospheres, stable climates, and the right conditions for liquid water. This means that even if we don't find an Earth-like exoplanet in the habitable zone, we might still find an Earth-like moon orbiting a larger planet. The implications of finding an exomoon with the right conditions for life are enormous. If we detect an exomoon with an atmosphere, liquid water, and the right chemical signatures, it would be one of the biggest discoveries in the history of astronomy. It would also force us to rethink our place in the universe. For decades, scientists have debated whether life is common or rare. If we find that moons as well as planets can support life, it would significantly increase the number of potentially habitable worlds in the galaxy. There's also the possibility that some exomoons could be home to completely different types of environments than anything we've seen before. Imagine a world where the sky is dominated by a massive planet filling half the horizon, where the day-night cycle is determined not just by the moon's rotation but also by its orbit around its planet. Some exomoons might have dual climates, one hemisphere that faces its planet constantly and another that experiences more variation in temperature and weather. We can also consider the potential for life to develop in unique ways on an exomoon. If a moon is tidally locked to its planet, meaning the same side always faces it, then life might evolve differently on each side. The side facing the planet might be bathed in reflected light, while the opposite side experiences regular day-night cycles. This could lead to different ecosystems, with certain life forms adapted to the conditions on one hemisphere while others thrive in completely different environments on the other side. If intelligent life were to evolve on an exomoon, it would have a completely different perspective on the universe than we do. Their night sky would be dominated by the massive presence of their host planet, possibly filling their sky with swirling storms, bands of clouds, or even a system of rings like Saturn's. Would they develop astronomy differently, given that their biggest celestial object isn't a distant sun but a planet that looms over them every night? Would they think of themselves as living on a planet, or would they always understand that they are part of a larger system? The search for the first confirmed exomoon is still ongoing, but when it happens, it will change everything. Whether it turns out to be a barren rock or a world teeming with potential, it will be the first step in a new era of discovery. Every new exomoon we find will give us a deeper understanding of how planetary systems form, how moons interact with their planets, and what conditions might allow life to emerge in the universe. And perhaps, one day in the distant future, humans might set foot on an exomoon orbiting a gas giant in a distant star system. Perhaps we will stand on its surface, looking up at the massive planet overhead, knowing that we have finally found a second home among the stars. The journey to find the first exomoon is just beginning, but the discoveries ahead will shape the future of space exploration in ways we can only imagine. The discovery of the first exomoon will not only redefine our understanding of planetary systems, but also challenge many of the assumptions we have about how celestial bodies interact in deep space. Scientists have long assumed that moons form in a way similar to how planets form, either through accretion from a disk of material surrounding a planet or through gravitational capture. However, the formation of exomoons could be much more complex, especially when considering the wide range of planetary systems that exist outside our solar system. For instance, some exoplanets orbit their stars at extreme distances, far beyond what we would expect for a planet to hold onto a moon. Other planets exist in tight orbits, close to their stars, where the gravitational forces could make it difficult for a moon to remain stable over long periods. The question then arises, are exomoons as common as we think, or are they rare phenomena that only exist under specific conditions? One of the strongest indicators that exomoons might be common comes from looking at our own solar system. Here, we see that large planets tend to have many moons. Jupiter has at least 95 known moons, Saturn has over 146, and even smaller planets like Neptune and Uranus host multiple moons. If this trend holds true for exoplanets, then gas giants discovered in other star systems could have their own families of moons, some of which might be as large as Earth, or even larger. But even if exomoons exist, detecting them is another challenge entirely. The search for exomoons is currently one of the most difficult tasks in exoplanet research. Unlike planets, which can cause noticeable dips in their star's light as they transit, exomoons create much subtler effects. If an exoplanet has a large moon, that moon might cause tiny, irregular shifts in the timing of the planet's transit across its star, a phenomenon known as transit timing variations, TTVs. These shifts are often just a few minutes or seconds long, making them incredibly difficult to measure. Another method used in the hunt for exomoons is transit duration variations, TDVs, which occur when a moon slightly changes the speed or angle at which an exoplanet crosses in front of its star. By carefully analyzing these small variations, astronomers can look for patterns that indicate the presence of a moon. However, this method requires extremely precise measurements and has so far only yielded possible candidates rather than confirmed discoveries. One of the most famous exomoon candidates to date is Kepler-1625b I, a potential moon orbiting the exoplanet Kepler-1625b. This discovery, announced in 2018, was based on data from NASA's Kepler Space Telescope. Astronomers noticed unusual transit timing variations in Kepler-1625b, suggesting that it might have a large moon. Follow-up observations with the Hubble Space Telescope provided additional evidence, showing that the exoplanet's transit lasted slightly longer than expected, a possible indication that a moon was trailing behind it. If Kepler-1625b I is confirmed, it would be a groundbreaking discovery. This potential exomoon is thought to be about the size of Neptune, making it far larger than any moon in our solar system. If true, this would raise an entirely new set of questions. Could moons form at such a large scale, or is this an unusual case where a smaller planet was somehow captured into orbit around a gas giant? What kind of conditions would exist on a moon of this size? Could it have an atmosphere, clouds, or even weather patterns? Another intriguing possibility is that some exomoons might have their own moons, small natural satellites orbiting around a larger moon, a phenomenon called a submoon or moonmoon. While no moon has been confirmed in our solar system, the idea is theoretically possible, and in other planetary systems, it might even be common. If an exomoon is large enough and has a strong gravitational pull, it could capture smaller bodies in orbit, creating a miniature version of a planet-moon system. The implications of finding such a complex system would be extraordinary. It would mean that the architecture of planetary systems is far more intricate than we ever imagined. Instead of just planets orbiting stars, we could have planets with large moons that host their own smaller moons, leading to a cascading hierarchy of celestial bodies. This would make the study of exomoons even more important, as they could be home to unique gravitational interactions and dynamic environments unlike anything we see in our solar system. Some scientists have even speculated that exomoons could play a key role in the development of extraterrestrial life. In our own solar system, moons like Europa and Enceladus are considered prime candidates for microbial life due to their subsurface oceans. If similar moons exist around exoplanets in habitable zones, they might also contain hidden oceans beneath thick layers of ice, heated by tidal forces and internal geological activity. These moons could act as cosmic laboratories, testing whether life can emerge in environments very different from Earth's. If exomoons are found with atmospheres, the next step would be to analyze their chemical composition. This could reveal the presence of oxygen, methane, or other gases associated with biological activity. A moon with an oxygen-rich atmosphere could indicate the presence of photosynthesis, while an unusual mix of gases could hint at more exotic forms of life. Some researchers have proposed that future telescopes like the James Webb Space Telescope or even next-generation observatories could directly detect these chemical signatures, offering the first real evidence of life beyond Earth. The discovery of an inhabited exomoon would be a game-changer, not just for science but for humanity as a whole. It would prove that life is not unique to Earth, and that biological processes can take root in environments that are very different from what we know. This could even have implications for the future of space exploration. If habitable exomoons exist, they could one day serve as stepping stones for interstellar travel, offering potential locations where future civilizations could build colonies or research outposts. But the search for exomoons is still in its infancy. Each year, new techniques and observational strategies are being developed to improve our ability to detect these elusive worlds. With every new exoplanet discovered, the potential for finding exomoons increases. And with future telescopes capable of even more detailed observations, the first confirmed exomoon may be closer than we think. When that moment arrives, it will be one of the most significant discoveries in the history of astronomy. It will open the door to new questions, new theories, and new possibilities. It will challenge our understanding of planetary systems and force us to reconsider how common habitable worlds might be. And perhaps, one day, we will look up at the night sky, knowing that out there, orbiting a distant planet in a distant star system, another moon, perhaps one not so different from our own, is waiting to be found. The search for the first exomoon is one of the most exciting and challenging frontiers in modern astronomy. While the discovery of exoplanets has revolutionized our understanding of planetary systems, the confirmation of an exomoon would take our knowledge even further. Scientists are using cutting-edge technology, new observational methods, and increasingly precise data analysis techniques to uncover these elusive celestial bodies. But despite the progress, the question remains, why haven't we definitively found one yet? One of the biggest hurdles in detecting an exomoon is that moons are much smaller than planets. When astronomers look for exoplanets, they primarily rely on the transit method, where a planet passes in front of its star, blocking some of its light. This creates a temporary dip in brightness that can be measured with telescopes like Kepler, TESS, and Hubble. However, an exomoon would create an even smaller dip, making it incredibly difficult to distinguish from the noise in the data. To overcome this challenge, researchers have turned to transit timing variations, TTVs, and transit duration variations, TDVs, as mentioned earlier. These methods rely on the fact that if an exoplanet has a moon, the moon's gravity will slightly alter the planet's motion, causing tiny but detectable shifts in its transit pattern. The problem is that these shifts can be incredibly subtle, sometimes just a few minutes or even seconds, making them almost indistinguishable from other natural variations in the star's light. One of the most promising candidates for an exomoon, Kepler-1625b I, was detected using this technique. The Kepler Space Telescope observed unusual transit timing variations in the exoplanet Kepler-1625b, hinting that it might be accompanied by a moon. The data suggested that this potential moon was massive, possibly as large as Neptune, which was surprising because no moon of that size exists in our own solar system. To confirm the finding, astronomers turned to the Hubble Space Telescope, which has even greater precision than Kepler. When Hubble observed Kepler-1625b, it saw additional evidence that something unusual was happening. The transit lasted slightly longer than expected, which could indicate that a moon was trailing behind the planet. But despite these promising signs, the data wasn't conclusive. Some scientists argue that the irregularities might be caused by other factors, such as instrumental noise or an unseen secondary planet in the system. This highlights one of the biggest difficulties in the search for exomoons, false positives. Because the signals we're looking for are so faint, it's easy to mistake random fluctuations in a star's brightness for the presence of a moon. To make matters worse, many of the exoplanets we're studying are hundreds or even thousands of light years away, meaning that even with the most powerful telescopes, we're working with very limited data. Despite these challenges, astronomers are not giving up. One approach being explored is looking for exomoons using radial velocity measurements. This method detects the slight wobble of a star caused by the gravitational pull of an orbiting planet. If a planet has a large moon, that moon could cause additional wobbles, revealing its presence. However, like TTVs and TDVs, the effect is extremely small, making it difficult to detect with current technology. Another potential strategy involves direct imaging, where telescopes attempt to capture actual pictures of exoplanets and their moons. This is extremely difficult because exoplanets are so far away and so faint compared to their parent stars. However, with the development of next-generation space telescopes like the James Webb Space Telescope, JWST, and future missions such as the Habitable Worlds Observatory, the chances of directly imaging an exomoon are increasing. One of the most exciting possibilities is that exomoons might not just exist, but they might also be habitable. In our own solar system, moons like Europa, Enceladus, and Titan are some of the best candidates for life beyond Earth. If similar moons exist around exoplanets in the habitable zone, they could have conditions suitable for life, such as liquid water, an atmosphere, and stable temperatures. Some researchers have even speculated that certain exomoons might be more habitable than their parent planets. For example, if a giant exoplanet orbits within a star's habitable zone, its moons might receive just the right amount of heat to support life. Additionally, tidal forces from the planet could generate internal heating, keeping subsurface oceans liquid even if the moon is far from its star. If a habitable exomoon is discovered, it could change everything we know about where life can exist in the universe. It would mean that we need to expand our search for extraterrestrial life beyond planets, and start seriously considering moons as potential hosts. In fact, some scientists argue that habitable moons might be even more common than habitable planets, simply because large gas giants are often found in exoplanet surveys, and many of them could have moons. But before we can answer these bigger questions, we need to confirm that exomoons exist in the first place. The search is ongoing, with new data being collected from telescopes around the world and in space. Every year, astronomers refine their techniques, improving our ability to detect the tiny signals that might reveal an exomoon. With advancements in technology and new missions on the horizon, the first confirmed exomoon might not be far away. And when that discovery happens, it will be one of the most groundbreaking moments in astronomy. It will show that moons are a fundamental part of planetary systems beyond our own. It will open up new possibilities for studying planetary formation, orbital dynamics, and even the search for life. And perhaps, just perhaps, it will be the first step in finding a place beyond Earth where life has taken root, hidden in the shadow of a giant planet, orbiting a distant star. As astronomers push forward with the search for the first confirmed exomoon, they are refining techniques, improving models, and looking at new ways to analyze the data we already have. One key question that still looms over the field is, what kinds of moons should we expect to find? In our solar system, moons come in all shapes and sizes. Some, like Earth's moon, are relatively large compared to their host planet. Others, like Phobos and Deimos around Mars, are small and irregularly shaped. Then there are the massive moons of Jupiter and Saturn, Ganymede, Titan, Europa, and Enceladus, which rival planets in size and complexity. If exomoons exist around exoplanets, they could be just as diverse, if not more so. One intriguing possibility is that exomoons might form in a way that's completely different from what we see in our solar system. Most moons here formed either from the debris of planetary collisions, like our moon, which likely formed when a Mars-sized object crashed into early Earth, or by being captured by a planet's gravity, like Neptune's moon Triton. But in other star systems, especially around massive exoplanets, new processes might be at play. For example, some scientists hypothesize that exomoons could form in the protoplanetary disks that surround young planets, much like how planets form around stars. If this is the case, some exomoons could be almost as large as Earth or even larger, potentially blurring the line between moons and planets. Others might form from material left over after the planet itself has finished forming, leading to smaller, irregularly shaped moons. Another fascinating idea is the possibility of rogue exomoons. Just as some planets have been ejected from their home star systems and now drift alone through the galaxy, it's possible that some moons could be torn away from their planets. These rogue exomoons might end up orbiting other planets, or even becoming miniature worlds on their own. If we discover an exomoon, the next major question will be, what is it made of? In our own solar system, moons range from rocky and barren, like our own moon, to icy and dynamic, like Europa and Enceladus. Some, like Titan, have thick atmospheres, while others, like Io, are covered in volcanic activity. If exomoons exist, they could have equally strange and diverse compositions. One particularly exciting possibility is that some exomoons could be ocean worlds. In our solar system, Europa and Enceladus are thought to have vast subsurface oceans hidden beneath their icy crusts. These oceans might even contain the conditions necessary for life. If similar moons exist around exoplanets, they could be among the best places in the universe to search for alien life. There's also the potential for exomoons with thick atmospheres, like Titan. Titan is unique in our solar system because it has rivers, lakes, and seas, not of water, but of liquid methane and ethane. Could there be exomoons out there with Earth-like atmospheres? What about moons with completely alien chemistry, unlike anything we've seen before? The challenge of answering these questions is that even if we find an exomoon, actually studying it in detail will be incredibly difficult. Unlike exoplanets, which we can sometimes analyze using techniques like spectroscopy to determine their atmospheric composition, exomoons are so small that they might not provide enough light for these kinds of studies. One way to work around this is by studying the way an exomoon affects its planet. If an exomoon has an atmosphere, it might leave subtle imprints on the light from the planet during a transit. Similarly, if an exomoon is volcanically active, it could release gases that influence the planet's atmosphere. Detecting these signals will require incredibly precise instruments, but with upcoming space telescopes, we might eventually be able to do it. The search for exomoons is also leading to new questions about planetary systems in general. In our solar system, gas giants like Jupiter and Saturn have many moons, while smaller planets like Earth and Mars have only a few. But in other star systems, could things be different? Could there be Earth-sized planets with multiple moons? Could gas giants have entire systems of moons, some of which are large enough to be planets themselves? There's even the question of whether double-moon systems might exist. In our solar system, no moon has its own moon. But in some extreme cases, could an exomoon have a tiny moon of its own? If so, what would that system look like, and how would it evolve over time? One of the most exciting aspects of the search for exomoons is that it forces us to rethink what we know about planetary formation. We used to believe that planetary systems formed in a very specific way, with small rocky planets near their star and gas giants farther out. But the discovery of exoplanets has shattered that idea. Now we know that planets come in all shapes and sizes, in all sorts of unexpected configurations. If we find exomoons, they could challenge our understanding in similar ways. For example, what if we find an exomoon orbiting a planet in a binary star system? How would the gravitational influence of two stars affect a moon's orbit? Could moons even exist in stable orbits in such chaotic environments? Or consider the idea of a habitable exomoon around a rogue planet, a planet that has been ejected from its star system and now floats through interstellar space. If such a planet had a large enough moon with an atmosphere, and if the moon was heated by tidal forces from the planet, could it still support life despite being far from any star? The deeper astronomers dig into the question of exomoons, the more possibilities emerge. Every potential detection brings new theories, new debates, and new ways of thinking about the universe. But despite all the excitement, the simple truth remains: we still haven't confirmed one. This is why the search for the first exomoon is one of the greatest unsolved mysteries in astronomy today. It's a question that sits right on the edge of discovery, close enough that we can almost taste it, but just out of reach. The coming years will be crucial in answering this question, with new telescopes, better technology, and more refined techniques bringing us closer to finding an exomoon for the first time. And when that moment comes, when the first exomoon is finally confirmed, it won't just be another scientific discovery. It will be a moment that reshapes our understanding of the cosmos, just as the discovery of exoplanets did. It will force us to rethink planetary formation, challenge our ideas about habitability, and maybe even open the door to finding life beyond Earth. Until then, the search continues. Every telescope, every dataset, every tiny shift in starlight brings us one step closer to solving this mystery. And when we do, it will be one of the most thrilling breakthroughs in the history of space exploration. One of the most frustrating aspects of the exomoon search is the constant battle against uncertainty. When Kepler-1625b I was first proposed as a candidate, the evidence seemed promising, but even the best data left room for doubt. The problem is that detecting something as small as a moon around an already distant planet is like trying to hear a whisper in the middle of a thunderstorm. There are so many variables: instrument sensitivity, data noise, the unpredictability of stellar activity, that it's easy to mistake an anomaly for a false signal. This is why astronomers are careful. In science, being wrong is part of the process, but no one wants to rush a discovery only to have it fall apart under scrutiny. Some astronomers believe that the hunt for exomoons will take longer than the hunt for exoplanets simply because the signals are much weaker. Even Kepler, which revolutionized exoplanet discovery, was never designed to find exomoons. It was optimized for detecting planets crossing in front of their stars, but its sensitivity was never intended for something as small as a moon tagging along with one of those planets. The problem is compounded by the fact that many exoplanet systems we've found so far are vastly different from our own. The first confirmed exoplanets were found around pulsars, something no one expected. Then came the discovery of hot Jupiters, gas giants orbiting so close to their stars that their atmospheres are being stripped away. These findings shattered our previous assumptions about planetary systems and forced astronomers to rethink how planets form and evolve. If exomoons follow the same pattern, if they exist in places we don't expect, or if they're nothing like the moons we see in our own solar system, then it's possible that our current methods simply aren't enough to find them. The transit method, which relies on detecting dips in starlight when a planet passes in front of its star, is great for finding exoplanets. But for exomoons, it has its limits. A moon's transit might overlap with its planets, making it harder to distinguish. Or worse, the moon might be too small to cause a measurable dip in brightness at all. This is where new techniques come in. One promising approach is looking at the way an exomoon might cause its planet to wobble. If a moon is large enough, it won't just orbit its planet. The planet will also move slightly in response to the moon's gravity. This subtle dance, called transit timing variations, TTVs, and transit duration variations, TDVs, could be a key indicator of an exomoon's presence. But even this method isn't foolproof. Other factors, like additional planets in the system or irregularities in the star itself, could mimic these variations. That's why astronomers aren't relying on just one approach. They're combining multiple methods, testing different models, and gathering as much data as possible before making a definitive claim. This is why the upcoming James Webb Space Telescope, JWST, is so exciting. With its incredible sensitivity and ability to analyze infrared light, JWST could provide a much clearer look at potential exomoons. Unlike Kepler, which was mainly a planet-hunting telescope, JWST is designed to study the atmospheres of distant worlds, detect faint signals, and refine our understanding of planetary systems. If an exomoon is out there, JWST might just be the tool to confirm it once and for all. But even if JWST finds an exomoon, the question of habitability remains. Could an exomoon support life? If so, what kind of life are we talking about? In our own solar system, some of the most promising places for life aren't planets at all, they're moons. Europa, one of Jupiter's largest moons, has an icy crust covering a massive subsurface ocean. Enceladus, a small moon of Saturn, shoots geysers of water vapor into space, suggesting that it, too, has an ocean beneath its surface. These moons are heated not by sunlight, but by tidal forces, the immense gravitational pull from their parent planets, which stretches and compresses their interiors, generating heat. If exomoons exist around giant exoplanets, could they have similar conditions? Could some of them be warm enough, with enough liquid water, to support microbial life? It's possible. In fact, some scientists argue that habitable exomoons might be more common than habitable planets. Gas giants are easier to detect than small, rocky planets, and if these giants have large moons, those moons could be potential candidates for life. In some cases, an exomoon might even be better suited for life than an Earth-like planet. Think about it. If a moon orbits a gas giant in the habitable zone of its star, it could receive warmth from both its star and from tidal heating. This could extend the habitable zone beyond what we typically consider, allowing life to exist in places we wouldn't normally expect. But there are challenges, too. One major problem is radiation. In our solar system, Jupiter and Saturn have intense radiation belts that could be lethal to life as we know it. If an exomoon orbits too close to its giant planet, it might be bombarded by high-energy particles, making it an inhospitable place. But if it orbits at just the right distance, it could be shielded from this radiation while still benefiting from tidal heating. Another factor to consider is atmosphere. A moon needs an atmosphere thick enough to retain heat and protect against cosmic radiation. Some moons, like Titan, have thick atmospheres, while others, like Europa, have almost none. If exomoons exist, their ability to support life could depend on whether they have an atmosphere and what it's made of. One of the most exciting possibilities is the idea of a double habitable system, a habitable exomoon orbiting a habitable planet. Imagine a giant, Earth-like world with a large, life-supporting moon. The two could share atmospheric material, exchange organic compounds, and create a dynamic environment where life thrives in ways we can't even imagine. But all of this remains speculative until we find that first exomoon. And this is what makes the search so thrilling. We're standing at the edge of discovery, knowing that the next few years could change everything we know about moons, planets, and even life itself. The search for exomoons isn't just about finding another celestial body, it's about expanding the boundaries of what's possible. It's about questioning everything we assume about planetary systems and recognizing that our own solar system might not be the template for how the universe works. And when that first exomoon is finally confirmed, when we have definitive proof that moons exist beyond our solar system, it will be one of the greatest moments in the history of astronomy. It will confirm that our universe is even more diverse and complex than we ever imagined. It will open the door to new questions, new discoveries, and new possibilities. Until then, the search continues. Every new telescope, every new data set, every new technique brings us one step closer. And when that moment of discovery finally arrives, it will be worth the wait. One of the biggest turning points in the search for exomoons is the growing realization that they might not just be rare but also incredibly diverse. In our solar system, we have moons of all kinds, some barren and cratered like our own, others icy and hiding vast subsurface oceans, and even one, Titan, with a thick atmosphere and liquid lakes on its surface. But what if the first confirmed exomoon turns out to be something we've never seen before? What if it completely redefines what we think moons can be? The possibility of capturing an exomoon in an entirely new category, one that challenges all our assumptions, adds another layer of excitement to this search. Just like how exoplanets shattered our understanding of planetary formation, exomoons could force us to rethink what it means to be a moon. Could some exomoons be massive enough to blur the line between a planet and a moon? Could some be rogue, drifting away from their host planets and floating freely through space? These are the kinds of questions that push astronomers to keep looking, even when the search is frustrating and uncertain. One of the biggest challenges in confirming an exomoon is ensuring that the signal isn't coming from something else entirely. Take Kepler-1625b I, the first major exomoon candidate. When its possible presence was announced, the scientific community immediately began debating whether the signal was truly from a moon or just an artifact of noisy data. The evidence seemed compelling. A strange shift in the transit timing of its host planet suggested that something was pulling on it, something that fit the profile of a massive exomoon. But here's the catch: the Kepler telescope, which first gathered the data, wasn't designed to detect exomoons. While Kepler revolutionized the search for exoplanets, its instruments were optimized for detecting dips in brightness caused by planets transiting their stars, not for the much more subtle influence of moons. This meant that even if an exomoon was present, the data would be noisy and uncertain. To verify Kepler-1625b I, astronomers turned to the Hubble Space Telescope, one of the most precise observatories ever built. Hubble had the capability to take a closer look at the system and provide more detailed data. When the follow-up observations came in, they showed an additional anomaly, a second dip in brightness that seemed to match what would happen if a moon was following its planet in orbit. This was an encouraging sign, but even with Hubble's superior precision, the data was still not conclusive enough. This is where things get complicated. In science, it's not enough to have evidence that hints at something. You need repeatable, undeniable proof. Even though Kepler-1625b I looked promising, the data was just on the edge of certainty, meaning that other explanations couldn't be ruled out. Some astronomers suggested that the signal might be the result of another planet in the system, or perhaps an error introduced by instrumental noise. To put it simply, science moves slowly for a reason. The last thing astronomers want is to rush to announce a discovery, only to have it fall apart under closer scrutiny. This is why the search for exomoons is so challenging. Unlike planets, which produce strong, obvious signals, moons are more subtle. Their influence is slight, their signals are faint, and they require extreme precision to detect. But the hunt continues, and with the next generation of telescopes coming online, we're entering a new era of exomoon research. The James Webb Space Telescope, for example, is expected to provide a massive leap forward. Unlike Kepler and Hubble, which mainly rely on visible light observations, Webb is designed to study the universe in infrared. This means it can see deeper, detect fainter objects, and analyze atmospheres in ways we've never been able to before. If an exomoon exists around a distant planet, Webb could help us study not just its presence, but also its composition. Is it rocky, like Earth's moon? Is it icy, like Europa? Could it have an atmosphere? Could it be warm enough to support liquid water? These are the kinds of questions Webb could help answer, pushing us even closer to understanding the true nature of exomoons. But there's another way we might find exomoons, and it doesn't involve transits or wobbles at all. Some astronomers believe that gravitational microlensing, a phenomenon where the gravity of a planet or moon bends and magnifies the light of a background star, could be the key to unlocking exomoon discoveries. If an exomoon passes in front of a distant star along with its planet, it could create a distinctive microlensing signal that reveals its existence. The beauty of this method is that it doesn't require a planet to be transiting in front of its star, meaning that it could help find exomoons in systems that we wouldn't be able to study with other techniques. However, gravitational microlensing events are rare and difficult to predict, making them a tricky but potentially groundbreaking tool in the search for exomoons. Despite all these challenges, one thing is clear: the discovery of the first confirmed exomoon is not a matter of if, but when. The universe is vast, and if our own solar system is any indication, moons should be incredibly common. We just haven't had the technology to find them, yet. When that first confirmed exomoon is finally detected, it will open a new chapter in our understanding of the cosmos. It will prove that moons are not unique to our solar system and that they might even be one of the most common types of celestial objects in the universe. More importantly, it will give us another potential place to search for life. If moons like Europa and Enceladus can harbor subsurface oceans here in our solar system, then there could be billions of similar moons orbiting gas giants in the habitable zones of their stars. Some might have atmospheres, some might have oceans, and some might even be more Earth-like than we ever imagined. And beyond just habitability, the discovery of exomoons will help answer some of the biggest questions about how planetary systems form and evolve. Do moons always form from the leftover material around a planet, like our own moon? Or can they be captured from elsewhere, like Neptune's largest moon, Triton? Could there be exomoons so massive that they blur the line between a planet and a moon entirely? The more we learn about exomoons, the more we'll understand the nature of planetary systems as a whole. Each new discovery will add another piece to the puzzle, giving us a clearer picture of how worlds form, how they change over time, and how they might support life. For now, we're still waiting for that first undeniable confirmation. But when it comes, it will be one of the biggest discoveries in the history of astronomy, one that reshapes our understanding of the universe and our place in it. The search for the first exomoon is more than just a scientific challenge. It's a journey into the unknown, a reminder that the universe is far stranger and more complex than we ever imagined. And with every new telescope, every new technique, and every new observation, we're getting closer to finding the answer. As astronomers refine their search methods and technology advances, one of the most exciting aspects of this quest is the potential for exomoons to reveal themselves in ways we haven't even considered yet. While the transit method and gravitational microlensing remain the primary tools in our arsenal, there are still countless unknowns in how these moons might behave and interact with their host planets. One of the biggest mysteries is whether exomoons could be far more common than we expect, but simply eluding detection due to their size, orbit, or composition. Some researchers suspect that our current methods are biased toward detecting only the largest exomoons, ones that would be more comparable to Neptune or Titan rather than something like our own moon. This means that if the first confirmed exomoon is finally found, it may not be a small, rocky body like we imagine, but a giant, planet-like moon orbiting a massive exoplanet. This opens up another intriguing possibility. What if some of these exomoons are large enough to have their own submoons? While known moons in our solar system have confirmed natural satellites of their own, there's no rule in physics that says it's impossible. If such moons exist around exomoons, their gravitational effects could create even more unique observational signatures, potentially leading to indirect detections. Beyond their basic existence, the potential variety of exomoons is staggering. Some could be shrouded in thick atmospheres, much like Titan. Others could be barren and cratered like Mercury. Some might even have active volcanism, like Jupiter's moon Io, with massive plumes of molten rock reshaping their surfaces over time. The more we learn about exomoons, the more we might discover environments that challenge our understanding of habitability itself. One of the most tantalizing aspects of exomoons is their potential to support life. Here in our own solar system, some of the most promising locations for extraterrestrial life aren't planets at all, they're moons. Europa and Enceladus, two icy moons of Jupiter and Saturn, respectively, contain subsurface oceans that could harbor microbial life. If moons like these exist around distant exoplanets, then our search for alien life might need to shift away from planets entirely and focus on their moons instead. A major question scientists are exploring is whether habitable exomoons could exist in a star's habitable zone. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where temperatures allow for liquid water to exist. If a gas giant with a large, rocky moon orbits within this zone, then that moon could have the right conditions for life. Unlike Earth, which gets its warmth directly from the sun, an exomoon could also receive energy from its host planet in the form of reflected light and tidal heating, forces that could keep its interior warm even if it were further from its star. This raises another fascinating question. Could an exomoon have an ecosystem entirely unlike anything we've seen before? If it orbits a gas giant, it might experience regular eclipses where the planet blocks out its star for extended periods. Would life evolve differently in such an environment? Would creatures adapt to long nights and bright days, much like deep-sea organisms on Earth that have evolved to survive in the darkness of the ocean depths? These are the kinds of possibilities that make the search for exomoons so thrilling. Another reason why exomoons are so important to study is the role they play in planetary systems. In our own solar system, moons have shaped the evolution of planets in ways we are only beginning to understand. Earth's moon, for example, stabilizes our planet's axial tilt, preventing extreme climate shifts. Without it, Earth's seasons would be far more chaotic, possibly making it less hospitable for life as we know it. If exomoons play a similar role in stabilizing exoplanets, they could be crucial for the development of habitable environments. Some researchers even speculate that an exomoon's gravitational influence could help regulate a planet's climate, much like our own moon influences ocean tides. In extreme cases, a large exomoon could even generate enough heat through tidal friction to sustain liquid water on its surface, even if the planet it orbits is in a colder part of its solar system. The more we search for exomoons, the more we realize how much we don't know. For instance, are exomoons more common around certain types of planets? Are they more likely to form around gas giants, or could we find them around rocky super-Earths as well? Could some exomoons even outlast their planets, surviving long after their host planets have been destroyed in stellar cataclysms? As we continue pushing the boundaries of what we can detect, future telescopes may finally provide the definitive evidence we need to confirm the first exomoon. The James Webb Space Telescope, with its ability to detect faint infrared signals, could help spot exomoons that are just out of reach with current technology. Meanwhile, proposed future missions like the Louvre telescope, if built, could bring even greater precision to the hunt, possibly allowing us to directly image exomoons in distant star systems. Another game-changer could be the development of more advanced artificial intelligence algorithms to analyze astronomical data. AI has already proven incredibly useful in exoplanet research, helping scientists sift through vast amounts of data to identify subtle signals that the human eye might miss. In the search for exomoons, AI could play a critical role in detecting faint, hidden patterns that point to their existence. Despite the difficulties, the search for exomoons continues to capture the imagination of astronomers and space enthusiasts alike. The discovery of the first confirmed exomoon will be a historic moment, one that reshapes how we view the universe. It will prove that moons are not just a feature of our solar system, but a fundamental part of planetary systems everywhere. But perhaps the most exciting possibility of all is that an exomoon could be the first place beyond Earth where we find evidence of life. Whether it's a frozen world with a hidden ocean or a warm, atmosphere-rich moon orbiting a gas giant in the habitable zone, the implications would be profound. It would mean that life is not unique to Earth, that the universe is teeming with possibilities, and that somewhere out there, beneath an alien sky, another world is waiting to be explored. The search for the first exomoon is about more than just finding another celestial body. It's about understanding the fundamental nature of the universe. Every step we take toward that discovery brings us closer to answering one of humanity's oldest questions: are we alone? While the search for the first confirmed exomoon continues, astronomers are beginning to realize that finding such a moon might be even more difficult than initially thought. Exoplanet detection has already pushed the limits of our observational capabilities, and exomoons, being significantly smaller and fainter, add an extra layer of complexity. However, the payoff for finding one is immense. If we confirm an exomoon, we won't just be learning about a single object. We'll be unlocking an entirely new category of celestial bodies that could reshape our understanding of planetary systems. One of the primary difficulties in detecting an exomoon is its incredibly subtle effect on its host planet. When astronomers look for exoplanets, they often rely on transit data, watching for tiny dips in a star's brightness as a planet passes in front of it. An exomoon, however, creates an even fainter dip in brightness, one that can be difficult to separate from background noise. In addition, the moon's orbit around its planet causes a small, unpredictable variation in the planet's transit signal, making it even harder to confirm the moon's existence with certainty. Another challenge is that many of the exoplanets we've detected so far are located in distant star systems, often hundreds or even thousands of light years away. At such distances, even the most advanced telescopes struggle to capture fine details. This is why many astronomers are looking closer to home, focusing on exoplanets within a few hundred light years of Earth, where our instruments have a better chance of detecting any accompanying moons. One of the best candidates so far, Kepler-1625b I, has provided tantalizing hints that exomoons might exist, but not enough to confirm them. This potential moon, orbiting a massive gas giant in a distant system, showed an unusual transit signal that some scientists interpreted as a moon's shadow trailing behind the planet. If real, this moon would be much larger than any in our own solar system, closer in size to Neptune. But without further data, its status remains unconfirmed, and astronomers remain cautious about declaring it the first known exomoon. So, what exactly would it take to confirm an exomoon? The process requires multiple observations using different methods to ensure that what we're seeing isn't just an anomaly. Astronomers need to detect the same signals repeatedly, ruling out alternative explanations like background stars or instrumental errors. This is why projects like NASA's James Webb Space Telescope, JWST, are so critical. JWST, with its high-precision instruments, is expected to revisit some of the most promising exomoon candidates in the coming years, potentially providing the final evidence needed to make a confirmation. Beyond JWST, the next generation of telescopes could revolutionize the hunt for exomoons entirely. The European Space Agency's Plato mission, set to launch in the 2020s, will focus on detecting Earth-sized exoplanets, but its advanced instruments could also improve our ability to spot exomoons. Meanwhile, future ground-based telescopes like the Extremely Large Telescope, ELT, in Chile could provide direct imaging capabilities that allow astronomers to see exomoons in greater detail than ever before. But what if we're looking in the wrong places? Some researchers speculate that the best place to find exomoons might not be around massive gas giants but around smaller, rocky exoplanets similar to Earth. If an Earth-sized exoplanet has a large enough moon, it might be more detectable than the faint signals we're struggling to confirm around distant gas giants. This could mean that our first confirmed exomoon might not be a giant, Neptune-like body but rather a rocky, Earth-like moon orbiting a planet in its star's habitable zone. The potential habitability of exomoons is one of the most exciting aspects of this search. In our own solar system, some of the most promising locations for extraterrestrial life aren't planets at all. They're moons like Europa, Titan, and Enceladus. These moons have subsurface oceans, thick atmospheres, and internal heat sources that could sustain life even in the absence of direct sunlight. If similar moons exist around exoplanets, they could dramatically expand the number of places in the universe where life might be found. One theory suggests that exomoons could even be more favorable for life than planets in some cases. If a moon orbits a large gas giant within the habitable zone, it might receive warmth from multiple sources: the star's light, the planet's reflected light, and the heat generated by tidal forces as the moon is pulled by the planet's gravity. This could create stable conditions for liquid water and potentially even a breathable atmosphere. Even more intriguing is the possibility of rogue exomoons, moons that were once part of a planetary system but became unbound, drifting freely through space. If such moons have thick atmospheres or internal heating mechanisms, they might be able to sustain liquid water and potentially even microbial life, even in the cold void of interstellar space. While the idea of life on a wandering moon may seem like science fiction, it's a scenario that some scientists are beginning to take seriously. As the search for exomoons continues, astronomers are refining their techniques and learning from past detections. Every failed attempt teaches us something new about how these moons might behave, how they interact with their host planets, and how we might eventually find them. The search is slow, but the rewards will be immense. Finding the first exomoon will be a groundbreaking moment in astronomy, proving that our solar system is not unique in having a rich and diverse population of moons. It will open the door to new studies on how moons form, how they evolve, and what role they play in planetary systems across the universe. More importantly, it could bring us one step closer to answering one of humanity's biggest questions: are we alone in the cosmos? If and when we confirm the existence of an exomoon, it will likely trigger an entirely new field of astronomical research. Right now, the study of exoplanets dominates the search for worlds beyond our solar system, but exomoons could add an entirely new dimension to this exploration. Instead of simply looking for planets in habitable zones, scientists would need to consider how moons might create their own habitable conditions. A gas giant orbiting slightly outside the habitable zone of its star might not seem like a promising location for life. But what if one of its moons had the right conditions to support liquid water? This could vastly increase the number of places in the universe where we might find life. But before we get ahead of ourselves, let's return to the challenge at hand: confirming an exomoon's existence. So far, the biggest issue remains the reliability of transit data. With exoplanets, we can observe multiple transits over time to confirm a planet's presence, but with exomoons, things get complicated. A moon's orbit around its planet can change slightly from one transit to the next, meaning that no two transits look exactly the same. This variation makes it difficult to separate the moon's signal from background noise. Even worse, if a moon orbits its planet at a highly inclined angle, it might not always transit the star at all, meaning we could easily miss it. There are alternative methods to find exomoons, but they come with their own challenges. One approach involves looking for the gravitational influence of an exomoon on its planet. When a large planet has a massive moon, the two bodies actually orbit a common center of mass. This creates a slight wobble in the planet's movement, which might be detectable through radial velocity measurements. However, these wobbles are incredibly subtle, and distinguishing them from the gravitational effects of other planets in the system is extremely difficult. Another possible detection method is direct imaging. This technique involves capturing a direct image of an exoplanet and searching for a faint companion nearby. However, the same problem that makes direct imaging of exoplanets difficult applies to exomoons as well. They are incredibly dim compared to their host stars. The brightness contrast between a planet and a moon is enormous, making it nearly impossible to detect an exomoon unless it is exceptionally large and far from its planet. Despite these difficulties, some researchers believe that the search for exomoons is on the verge of a breakthrough. The James Webb Space Telescope, JWST, has already begun collecting data that could provide clearer evidence of an exomoon. Its advanced instruments allow astronomers to analyze exoplanet atmospheres in greater detail than ever before, and in some cases, this could reveal the presence of a moon. If an exoplanet's transit data shows unexpected chemical signatures, such as additional atmospheric absorption that doesn't match the planet alone, it might hint at a moon with its own atmosphere. Additionally, upcoming missions like the European Space Agency's Aerial Telescope and the Habitable Worlds Observatory could contribute to the search. These telescopes will be optimized for studying exoplanet atmospheres, and while they aren't specifically designed to detect exomoons, their high-precision measurements could make accidental discoveries possible. Another exciting avenue of research involves studying the effects of exomoons on their host planets' climates and atmospheres. If a large exomoon has an atmosphere, it could influence the overall climate of the planet-moon system in unexpected ways. Tidal interactions between the planet and moon could generate internal heating, affecting both worlds' geological activity and potentially creating subsurface oceans. In our own solar system, we see evidence of this effect in moons like Europa and Enceladus, where tidal forces from Jupiter and Saturn create internal heat that keeps their subsurface oceans from freezing solid. If a similar process is happening in exomoon systems elsewhere in the galaxy, it could mean that liquid water, one of the key ingredients for life, is far more common than we previously thought. One of the most exciting possibilities is that an exomoon could support its own biosphere, independent of its host planet. On Earth, life thrives in some of the most extreme environments imaginable, from hydrothermal vents on the ocean floor to the frozen tundras of Antarctica. If a moon has a thick atmosphere, stable liquid water, and a source of energy, it could theoretically host life even in conditions that seem inhospitable to humans. This raises an interesting question. If we do find an exomoon, how will we know if it harbors life? Unlike planets, which have large surface areas where biosignatures might be detectable, a moon's smaller size makes it harder to study in detail. Scientists would need to look for indirect signs of life, such as unusual atmospheric compositions, unexpected chemical reactions, or energy emissions that can't be easily explained by natural processes. One of the most intriguing ideas is that an exomoon could have an artificial signature, evidence of alien technology. If an advanced civilization existed on an exomoon, it might produce artificial lights, heat emissions, or radio signals that could be detected from Earth. While this might sound far-fetched, astronomers are already considering ways to search for these technosignatures in exoplanet systems, and if an exomoon is home to intelligent life, it could be one of the first places we find evidence of extraterrestrial civilizations. But even if we don't find alien life, confirming an exomoon would be a monumental achievement. It would show that the formation of moons is a common process across the universe, reinforcing the idea that our solar system is not unique. It would also help refine our models of planetary system formation, giving us a better understanding of how planets and moons evolve over time. As we push the boundaries of what's possible with modern telescopes, the search for exomoons remains one of the most exciting frontiers in astronomy. Each new discovery brings us closer to answering fundamental questions about the universe. How common are moons in other systems? Can they support life? And could an exomoon be the first place we find evidence of extraterrestrial intelligence? For now, the search continues. But with each new observation, each new piece of data, we move one step closer to a breakthrough that could change our understanding of the cosmos forever. If an exomoon is finally confirmed, it could also reshape our understanding of planetary system dynamics. In our own solar system, moons come in a wide variety of sizes, compositions, and orbital behaviors. Some, like Earth's moon, are thought to have formed from a massive impact. Others, like the Galilean moons of Jupiter, likely formed from the same disk of material that created their parent planet. Then there are captured moons, objects that originally formed elsewhere in the solar system before being gravitationally trapped by a larger planet. If exomoons exist beyond our solar system, they might follow similar patterns, or they might introduce entirely new moon formation processes that we've never considered. One of the biggest questions is whether exomoons could form around rogue planets, planets that drift through space without orbiting a star. If a rogue planet had a moon, it would essentially be a miniature solar system moving through the galaxy on its own. This raises fascinating possibilities for what kinds of conditions might exist on such a world. Without a nearby star, the planet itself would likely be cold and dark, but a large enough moon with an atmosphere and internal heating could still support liquid water. Some scientists have even speculated that life could survive on these rogue moons, using geothermal heat or other non-solar energy sources. But let's bring the focus back to the current search for exomoons. So far, the most promising candidates have all been found using the transit method. However, a major challenge remains: distinguishing an exomoon signal from other possible explanations. One possibility is that what we think is an exomoon is actually a second, smaller planet orbiting in a binary configuration with the larger planet. These so-called Trojan planets could create transit signals that mimic those of moons, making it difficult to be sure what we're seeing. To solve this problem, astronomers need as much data as possible. The best way to confirm an exomoon is through repeated observations over long periods of time, looking for consistent patterns in how the planet's transit changes. If an exomoon is truly present, its gravitational pull should create a predictable wobble in the planet's movement that can be tracked over multiple observations. However, this requires extremely precise measurements, which is why scientists are eagerly awaiting the results from the James Webb Space Telescope and other upcoming missions. Another potential breakthrough could come from studying planetary ring systems. In our own solar system, planets like Saturn, Jupiter, Uranus, and Neptune all have extensive ring systems, and there's reason to believe that exoplanets might as well. Some researchers speculate that rings could actually be the remnants of destroyed exomoons, moons that got too close to their planet and were torn apart by tidal forces. If this is true, studying exoplanet rings could provide indirect evidence of exomoon formation and destruction, even if we never directly observe the moons themselves. The presence of exomoons could also affect planetary atmospheres in surprising ways. On Earth, our moon plays a crucial role in stabilizing the planet's axial tilt, preventing wild climate swings. If exomoons are common, they might have similar effects on their host planets, making some worlds more stable and habitable than they otherwise would be. This means that when we search for potentially habitable exoplanets, we might also need to consider whether they have exomoons that contribute to their long-term stability. And then there's the question of habitability itself. Could an exomoon be a better candidate for life than its parent planet? If a massive gas giant exists in the habitable zone of a star, its surface would be inhospitable, but its moons might be another story. A large enough moon with an atmosphere, water, and the right temperature conditions could be an ideal location for life to evolve. Some researchers have even suggested that exomoons could be the most common type of habitable world in the universe. If we do find an exomoon with signs of habitability, it could change everything we know about the search for life beyond Earth. Instead of focusing solely on planets, we might need to shift our attention to the moons orbiting them. And if we ever discover alien life, there's a real possibility that it won't come from an exoplanet at all. It could come from an exomoon. The search continues, and with each new observation, we inch closer to the answer. Whether it takes years or decades, the discovery of the first confirmed exomoon will be a defining moment in the history of astronomy. Until then, scientists will keep looking, analyzing every anomaly, every unexpected dip in starlight, every strange gravitational wobble, because somewhere out there, the first exomoon is waiting to be found. The search for the first exomoon is not just about proving their existence, it's about expanding the boundaries of what we know about planetary systems, habitability, and even the formation of life. If exomoons are out there, they might be more than just sidekicks to their planets. They could be homes for alien ecosystems, laboratories for extreme planetary physics, or even clues to understanding how our own solar system came to be. One of the biggest reasons exomoons remain elusive is the difficulty of distinguishing their signals from other cosmic noise. When looking for exoplanets, scientists rely on the transit method, watching for small dips in a star's brightness as a planet passes in front of it. But an exomoon is much smaller than a planet, meaning its transit would be even harder to detect. Even if a large exomoon were to transit along with its planet, the combined dip in brightness would be so subtle that it would be difficult to separate the two. To make things even trickier, the presence of an exomoon would cause irregularities in the planet's own transit. Instead of a perfectly consistent dip in brightness, a planet with a moon would create slight variations in the timing and depth of the transit, as the moon's gravitational influence tugs on the planet. These variations, known as transit timing variations, TTVs, and transit duration variations, TDVs, are one of the main ways scientists try to infer the presence of exomoons. But even these clues are not always definitive, as other factors like the gravitational influence of nearby planets can create similar irregularities. To increase the chances of detecting an exomoon, astronomers need repeated, high-precision observations of exoplanetary systems. This is why Kepler-1625b I, the first serious exomoon candidate, was such an exciting discovery. When astronomers reanalyzed Kepler data and later followed up with Hubble, they noticed something unusual. The planet Kepler-1625b wasn't following a perfectly predictable orbit. Its transit had small but noticeable deviations, and after the planet had fully passed in front of its star, there was an additional, smaller dip in brightness, potentially caused by a massive moon following behind. If confirmed, this exomoon would be unlike anything we've seen before. It's estimated to be Neptune-sized, orbiting a planet that is several times larger than Jupiter. This means that, unlike in our solar system where moons are much smaller than their planets, exomoons in other systems might be massive, possibly even forming miniature planetary systems of their own. If a moon as large as Neptune can exist around a gas giant, could it have its own atmosphere? Could it have clouds, weather, or even an internal ocean? These are the kinds of questions that drive scientists to keep searching. But skepticism remains. Despite the promising evidence, Kepler-1625b I is not yet fully confirmed. The data could be affected by instrumental noise, or the observed irregularities might be caused by another, less obvious phenomenon. This is why the field of exomoon research is still waiting for that one undeniable detection, one that can be confirmed with multiple methods, across multiple observations. Upcoming telescopes, like the James Webb Space Telescope, the European Space Agency's Plato mission, and NASA's future exoplanet observatories, will play a critical role in the next phase of exomoon hunting. With their higher precision and ability to analyze exoplanetary atmospheres, these missions might not only detect exomoons but also determine their compositions. Could an exomoon have an atmosphere rich in oxygen or methane, hinting at biological activity? Could we detect seasonal changes, storms, or cloud patterns on an exomoon? These are questions we may be able to answer in the coming decades. And beyond just detection, exomoons might change the way we think about the habitability of the universe. If moons can have thick atmospheres, liquid water, and internal heat sources, they could be more common sites for life than planets themselves. Imagine an Earth-sized exomoon orbiting a massive gas giant in the habitable zone of a star. Instead of one planet being habitable, the entire system could have multiple habitable worlds. If that's the case, then when we look at exoplanetary systems, we might be underestimating the true number of potentially habitable worlds. A system with 3 giant planets might not just have 3 chances for life. It could have a dozen, if each of those planets has large moons capable of supporting life. This could mean that the galaxy is teeming with habitable worlds, many of which might be hiding in plain sight. The search for exomoons is, in many ways, the next frontier of exoplanet research. We've already confirmed thousands of exoplanets, but exomoons remain just beyond our grasp, tantalizing, mysterious, and waiting to be discovered. Every new telescope, every new dataset, every improvement in our ability to analyze faint signals brings us closer to that moment when we finally detect an exomoon with absolute certainty. And when that moment comes, it won't just be a scientific breakthrough, it will be a paradigm shift. We will have proof that moons beyond our solar system exist, and with that knowledge, a whole new universe of possibilities will open up. What kinds of worlds are out there? What surprises do these distant moons hold? And most importantly, could one of them, right now, be home to something more than just rock and ice? Could an exomoon, orbiting a distant gas giant, hold the answer to the biggest question of all? The search continues, and the discoveries to come might be even more incredible than we can imagine. The search for exomoons is not just an extension of exoplanet research, it's a doorway into entirely new possibilities for what planetary systems can look like. For centuries, astronomers assumed that our solar system was a typical example of how planets and moons should be arranged. But the discovery of thousands of exoplanets has shattered that assumption. We've found planets in places they shouldn't be, orbiting in ways we never expected. If exomoons follow the same pattern, they could redefine our understanding of habitability, planetary formation, and even the very nature of what makes a world capable of supporting life. One of the most fascinating aspects of exomoons is the sheer variety they could exhibit. Here in our solar system, we have a diverse collection of moons: icy moons like Europa and Enceladus, volcanic worlds like Io, massive atmospheres like Titan, and even moons with underground oceans that could harbor life. If exomoons exist around exoplanets, they could be even more extreme. Some could be as large as Earth, orbiting gas giants in the habitable zone of their star. Others could be mini Neptunes with thick atmospheres, defying our expectations of what a moon should be. There could even be rogue moons, moons that were ejected from their planetary systems and now drift through space alone. One of the biggest implications of finding an exomoon is its potential impact on our search for extraterrestrial life. Planets orbiting close to their stars often suffer from extreme radiation, tidal locking, and other conditions that make life unlikely. But an exomoon orbiting a gas giant could be shielded from these dangers. The gravitational interactions between the moon and its planet could generate internal heat, keeping subsurface oceans liquid even in the coldest parts of space. This is exactly what happens with Europa and Enceladus, moons that, despite being far from the Sun, have subsurface oceans that could harbor microbial life. Now, imagine a giant exoplanet in the habitable zone of its star, with several large moons orbiting it. Each of these moons could have its own climate, weather systems, and even life forms. If a civilization were to evolve on one of these moons, they wouldn't just have one celestial body to explore, they'd have an entire planetary system right in their backyard. This could change the way we think about space travel, planetary colonization, and even the concept of home for an intelligent species. But before we can speculate on the possibilities of exomoon civilizations, we have to prove that exomoons exist. This is where the challenge comes in. Detecting an exoplanet is already incredibly difficult. Detecting a moon that is much smaller and fainter is even harder. The Kepler Space Telescope gave us our first real shot at finding exomoons, and while its data hinted at the existence of Kepler-1625b I, it wasn't enough to confirm it. The Hubble Space Telescope provided additional observations, but even those weren't conclusive. The signal was there, but it wasn't strong enough to be definitive. This is why future telescopes are so important. The James Webb Space Telescope, JWST, has the sensitivity to detect even smaller dips in starlight, which could finally give us the evidence we need. But even JWST has limitations. It wasn't designed specifically for exomoon hunting, so researchers have to be strategic about how they use its time and resources. Future missions like the proposed LUVOIR, Large Ultraviolet Optical Infrared Surveyor, and Habitable Worlds Observatory, might finally provide the level of precision needed to confirm exomoons once and for all. If and when we find our first exomoon, it will be a historic moment, not just for astronomy, but for our understanding of the universe. It will prove that our solar system is not unique, that moons are common features of planetary systems, and that we have only scratched the surface of what is possible. But beyond that, it will open up a new field of study, with new questions to answer. How common are exomoons? Could they outnumber planets? Could some be large enough to be considered planets themselves? Could they have atmospheres, oceans, and even life? The search for the first exomoon is not just a quest for another celestial object, it is a search for the unknown. And as history has shown us, every time we push the boundaries of what we know, we end up discovering something even more incredible than we ever imagined. The search for exomoons is a challenge unlike any other in modern astronomy. While the hunt for exoplanets has become more refined with each passing year, detecting a moon around one of these distant worlds is an entirely different level of difficulty. The problem comes down to size, distance, and the methods we use to detect celestial objects beyond our solar system. Exoplanets are hard enough to find, requiring precise observations of how they interact with their host stars. But exomoons are even smaller, often hidden within the light signatures of the planets they orbit, making them nearly impossible to detect with current technology. Most exoplanets are discovered using the transit method, where astronomers observe a star and measure the tiny dip in brightness that occurs when a planet crosses in front of it. But a moon orbiting that planet would create an even smaller, more subtle dip, one that could easily be lost in the noise of observational data. To make matters worse, moons don't always orbit their planets in a perfect, predictable way. Their movements are influenced by the gravitational pull of their host planet, as well as the star itself, causing variations that make their detection even more complicated. That's why the case of Kepler-1625b I was so groundbreaking. When astronomers first noticed an unusual dimming pattern in the Kepler-1625 system, they suspected something was different. The planet Kepler-1625b, a massive Jupiter-like gas giant, was already unusual in its own right, but its light curve, the way the star's brightness changed as the planet passed in front of it, had irregularities that couldn't be explained by just the planet alone. It hinted at the presence of a companion, something smaller that was also blocking some of the star's light. Further observations with the Hubble Space Telescope seemed to confirm this possibility. The timing of Kepler-1625b's transit was slightly off, as if something was tugging at it, slowing it down. This kind of shift is exactly what we would expect if a large moon were orbiting the planet. The data also suggested a second, smaller dip in brightness following the main transit event, potentially the moon passing in front of the star after the planet. It was the strongest evidence yet of an exomoon, but there was still uncertainty. The data wasn't conclusive, and scientists needed more observations to be absolutely sure. One of the biggest issues with confirming Kepler-1625b I is that the Kepler telescope, which originally collected the data, is no longer operational. This means that astronomers can't simply take another look whenever they want. Instead, they have to rely on space telescopes like Hubble or James Webb, which have limited time available for exomoon searches. Every minute of telescope time is highly valuable, with multiple scientific teams competing to observe different targets. This makes exomoon hunting an uphill battle, as researchers must justify why their observations should take priority over other high-profile studies. But despite these challenges, scientists remain determined. The search for exomoons isn't just about confirming one particular candidate. It's about proving that moons exist outside our solar system at all. If Kepler-1625b I is real, it would be a groundbreaking discovery, changing the way we think about planetary systems. It would show that moons are not unique to our solar system and that they likely play a significant role in shaping planetary evolution across the galaxy. More importantly, it would open the door for even more discoveries. If we can find one exomoon, we can find others. And if we can find others, we can start to answer bigger questions. Are exomoons common? Do they form the same way as moons in our solar system? Could any of them be habitable? Could an Earth-sized exomoon exist around a giant planet in a star's habitable zone? These are the kinds of questions that drive scientists forward, pushing the boundaries of what we know about the universe. While we may not have definitive proof of an exomoon yet, the search is far from over. With the next generation of telescopes and advances in observational techniques, we may soon get the answer we've been waiting for. And when that moment comes, it will mark the beginning of a whole new chapter in our understanding of the cosmos. The search for exomoons is one of the most tantalizing mysteries in modern astronomy. While we've confirmed thousands of exoplanets, the existence of moons beyond our solar system remains unproven. If exomoons do exist, and there's strong reason to believe they do, they could be just as diverse and fascinating as the planets they orbit. Some could be massive, Earth-sized worlds orbiting gas giants, while others might be icy, ocean-covered bodies teeming with the conditions necessary for life. The implications of finding an exomoon go far beyond simple classification. It could reshape our understanding of planetary formation, habitability, and even the likelihood of alien life. Kepler-1625b I remains the most compelling candidate for the first known exomoon. But why is it so difficult to confirm? The answer lies in the limitations of our current detection methods. Most exoplanets are discovered using the transit method, which looks for periodic dips in a star's brightness as a planet crosses in front of it. A moon, being much smaller than its host planet, would create an even fainter dip in brightness, making it much harder to detect. Not only that, but moons don't transit in a perfectly predictable way. They orbit their planets in complex patterns, introducing variations that make detection even more challenging. When astronomers first analyzed the data from Kepler-1625b, they noticed something strange. The planet's transit across its star wasn't as straightforward as expected. The timing was slightly off, as if something was tugging at the planet, slowing it down. This is exactly what we would expect if a large moon were orbiting the planet, pulling on it with its own gravitational force. Further analysis revealed another irregularity. After the planet finished transiting, there appeared to be a second, smaller dip in brightness, suggesting that something else, a moon, was following behind it. To confirm this finding, scientists turned to the Hubble Space Telescope. Hubble provided a clearer view, and the results seemed to support the idea that a moon was present. But the data still wasn't conclusive. The signal was weak, and there was a chance that it could have been a statistical anomaly rather than a real moon. Without further observations, astronomers couldn't say for certain whether Kepler-1625b I was an actual moon or just an illusion created by noisy data. One of the biggest challenges in exomoon detection is the limited availability of powerful telescopes. The Kepler telescope, which originally collected the data on Kepler-1625b, is no longer operational. This means that astronomers can't simply take another look whenever they want. Instead, they have to rely on space telescopes like Hubble or James Webb, which have limited time available for exomoon searches. Every minute of telescope time is highly valuable, with multiple scientific teams competing to observe different targets. This makes exomoon hunting an uphill battle, as researchers must justify why their observations should take priority over other high-profile studies. Despite these challenges, scientists are pushing forward. The search for exomoons isn't just about proving that Kepler-1625b I exists, it's about answering larger questions about planetary systems as a whole. If exomoons are common, it would suggest that our solar system is not unique and that moons could play a major role in shaping planetary environments throughout the galaxy. It would also raise exciting possibilities for habitability. One of the most intriguing ideas is that exomoons could actually be better places for life than planets. Many exoplanets orbit very close to their stars, making them subject to extreme radiation and tidal locking, where one side is always facing the star while the other is in permanent darkness. But a moon orbiting a giant planet could be shielded from some of these effects. The gravitational interactions between the moon and its planet could generate internal heat, keeping subsurface oceans liquid even in the coldest regions of space. In our own solar system, we see this with moons like Europa and Enceladus, both of which have vast underground oceans that could harbor microbial life. If similar moons exist around exoplanets, they could be among the best places to look for alien life. Imagine a massive exoplanet in the habitable zone of its star, surrounded by several large moons. Each of these moons could have its own atmosphere, climate, and possibly even life forms. If an intelligent civilization were to evolve on one of these moons, they wouldn't just have one celestial body to explore, they'd have an entire planetary system right next door. But before we can speculate too much, we need to prove that exomoons exist in the first place. That's why astronomers are eagerly awaiting the next generation of space telescopes. The James Webb Space Telescope, JWST, has the sensitivity to detect even smaller dips in starlight, which could finally provide the evidence needed to confirm an exomoon. However, even JWST has its limitations. It wasn't specifically designed for exomoon hunting, so researchers have to be strategic about how they use its time and resources. Looking ahead, future missions like LUVOIR, Large Ultraviolet Optical Infrared Surveyor, and the Habitable Worlds Observatory could provide the level of precision needed to detect exomoons with confidence. These telescopes will be capable of capturing more detailed light curves, making it easier to distinguish between planetary and lunar signals. With their help, we could soon move from speculation to confirmation. If and when we do find the first exomoon, it will mark a turning point in astronomy. It will prove that moons are a natural part of planetary systems, just as planets are a natural part of star systems. But beyond that, it will open up a whole new field of study. How do exomoons form? Are they as diverse as the moons in our solar system? Could any of them support life? And could some be so large that they blur the line between planets and moons? The search for the first exomoon is more than just a hunt for another celestial body. It's a quest to understand the complexity of the universe itself. Every time we think we have a clear picture of how planetary systems work, new discoveries force us to rethink everything. And if exomoons exist, they could be among the most fascinating and unexpected worlds in the cosmos. As our technology improves and our ability to study distant planets becomes more refined, it's only a matter of time before we find the answer. And when that moment comes, it will be one of the most significant discoveries in the history of astronomy, a confirmation that the universe is far more intricate, mysterious, and full of possibilities than we ever imagined. The implications of finding an exomoon stretch far beyond simply adding another category to our growing list of celestial objects. If exomoons are common, they might play a significant role in shaping planetary environments, influencing their climates, and even affecting their potential for life. The discovery of the first confirmed exomoon would be like opening a new chapter in the book of planetary science, one that could fundamentally reshape our understanding of how planetary systems evolve. One of the biggest mysteries surrounding exomoons is their formation. In our own solar system, moons form in three primary ways. Some, like Earth's moon, are thought to be the result of giant impacts, where a collision between two planetary bodies throws debris into orbit, eventually coalescing into a moon. Others, like the moons of Jupiter and Saturn, are believed to have formed from the same disk of gas and dust that gave rise to their parent planets, much like a miniature version of planetary formation around a star. And then there are captured moons, like Neptune's Triton, which was likely a wandering object that got pulled into the planet's gravitational field. If exomoons form in the same ways, we could expect to see a wide range of moon types in exoplanetary systems. Some might be barren and rocky, while others could be rich in water and organic materials. But there's also the possibility that exomoons form through processes we haven't yet observed. Since we've only studied planetary formation in our own solar system, we don't know if the same rules apply everywhere. The discovery of an exomoon could challenge our current models and force us to rethink what we thought we knew. One particularly fascinating idea is the possibility of supermoons, moons that are as large as, or even larger than, Earth. In our solar system, the largest moon is Ganymede, which is bigger than Mercury but still much smaller than Earth. But what if, in another star system, a moon formed that was the size of our planet, complete with an atmosphere, liquid water, and a stable climate? Such a world would blur the line between planet and moon, raising new questions about classification and habitability. If a large exomoon were found orbiting a gas giant in the habitable zone of its star, it could be one of the most promising places to search for extraterrestrial life. Unlike many exoplanets, which are often subjected to extreme radiation or tidal locking, a habitable zone exomoon could enjoy a more stable environment, protected by its planet's magnetic field and warmed by tidal heating. This could make it a more favorable place for life than even some exoplanets in the same region. Tidal heating is another key factor that could make exomoons incredibly interesting. In our solar system, we see this process at work on moons like Io, Europa, and Enceladus. These moons are squeezed and stretched by their planet's gravity, generating internal heat that can sustain subsurface oceans. If the same process is occurring on exomoons in distant star systems, it means that even moons outside of traditional habitable zones could have liquid water beneath their icy crusts. This brings up another major question: could an exomoon ever be more habitable than its host planet? Most habitable zone exoplanets we've discovered so far are either large, rocky super-Earths or gas giants. If a gas giant is in the habitable zone, it's unlikely to support life itself, but its moons could be another story. In a way, these moons could act as second Earths, places where conditions are just right for liquid water, complex chemistry, and maybe even biological evolution. The search for exomoons is still in its infancy, but as our detection methods improve, we're getting closer to an answer. The James Webb Space Telescope is expected to play a key role in this search, with its ability to measure light curves with unprecedented precision. If an exomoon exists around a transiting exoplanet, JWST might be able to detect its signature more clearly than Kepler or Hubble ever could. However, even with JWST, the search is still extremely challenging. Exomoons don't just follow their planets in neat, predictable paths. Their orbits can be highly variable, influenced by the gravitational pull of their planets and other nearby moons. This means that even if a telescope detects a possible moon, scientists have to rule out other possibilities, such as random fluctuations in the data or distortions caused by instrumental noise. Another exciting possibility is direct imaging, which is a method that allows telescopes to capture actual pictures of exoplanets and potentially their moons. Right now, direct imaging is only possible for massive exoplanets that orbit far from their stars, but future telescopes could improve this technique. If we could directly image an exomoon, it would provide definitive proof of their existence and give us a better understanding of their characteristics. So, what happens if we do confirm the first exomoon? The discovery would likely spark a wave of follow-up studies, as astronomers try to determine how common exomoons are and what kinds of worlds they might be. It would also prompt the development of new models to explain their formation and evolution. And if exomoons turn out to be abundant, it would mean that our solar system is not an outlier, but rather a small piece of a much larger pattern. In the grand scheme of things, the search for exomoons is about more than just cataloging celestial objects. It's about understanding how planetary systems work, how worlds form and interact, and ultimately, where we might find life beyond Earth. Every new discovery brings us one step closer to answering the biggest questions in astronomy. Are we alone? Is Earth special, or just one of many habitable worlds? And what surprises does the universe still have in store for us? The search for the first exomoon is a long and difficult journey, but it's one worth taking. With every new telescope, every new dataset, and every new breakthrough, we move closer to solving this mystery. And when we finally do, it will be a moment that redefines our understanding of the cosmos, proving once and for all that the universe is far more complex, dynamic, and full of wonders than we ever imagined. The confirmation of the first exomoon wouldn't just be a monumental achievement in astronomy. It would reshape our perspective on planetary systems and open up entirely new areas of research. Right now, we're only scratching the surface, and the sheer difficulty of detecting an exomoon means that when we do find one, it will likely be just the beginning. There could be an entire population of exomoons out there, hiding in the shadows of their planets, waiting to be discovered. One of the most exciting implications of finding an exomoon is what it could tell us about the formation of planetary systems beyond our own. For decades, our understanding of moon formation has been based on our solar system. But what if exomoons form differently in other systems? What if they have unique properties we've never seen before? If we find an exomoon that doesn't fit into any of the formation categories we currently know, collision, disk accretion, or capture, it would mean there are entirely new processes at play. And that leads to another big question: how stable are exomoons over time? In our solar system, some moons have remained in stable orbits for billions of years, while others have been ejected due to gravitational interactions. The same could be happening in exoplanetary systems, but on a much grander scale. If exomoons are frequently lost, it could explain why they're so hard to detect. It's possible that many planets had moons at some point but lost them due to gravitational interactions with other planets, or their host stars. This raises the possibility that some exoplanets we observe today were once part of more complex systems with multiple moons, some of which may have escaped into interstellar space or been destroyed in collisions. Another key factor in the search for exomoons is their potential effect on their host planets. In our own solar system, Earth's moon plays a crucial role in stabilizing our planet's axial tilt. Without the moon, Earth's tilt would likely vary much more over time, leading to extreme climate shifts that could make life as we know it much harder to sustain. If exomoons exert similar stabilizing effects on their host planets, they could play an essential role in making certain exoplanets more habitable. There's also the question of whether exomoons could have atmospheres. In our solar system, most moons don't have substantial atmospheres, except for Titan, Saturn's largest moon, which has a thick nitrogen-rich atmosphere. If Titan can have an atmosphere, could there be exomoons in other star systems with even more complex atmospheres, possibly capable of supporting life? The presence of an atmosphere could have significant implications for an exomoon's climate and habitability. If an exomoon orbits within a gas giant's magnetosphere, it could be shielded from harmful stellar radiation, creating a more stable environment for life. Alternatively, some exomoons could have magnetospheres of their own, protecting them from cosmic radiation and stellar winds. Another factor to consider is the role of tidal heating. In our solar system, tidal forces drive geological activity on moons like Io and Europa. Io, which orbits close to Jupiter, experiences extreme tidal heating that keeps its interior molten and fuels its massive volcanic eruptions. Europa, on the other hand, has a subsurface ocean kept warm by tidal forces. If similar tidal heating occurs on exomoons, it could create environments with liquid water even in star systems where the planet itself is too cold to support life. This means that exomoons might actually expand the habitable zone of a planetary system. Traditionally, astronomers define the habitable zone as the region around a star where conditions allow for liquid water on the surface of a planet. But if an exomoon can have liquid water due to tidal heating, it doesn't need to be in the traditional habitable zone. It could be orbiting a gas giant far from its star, yet still have a warm, subsurface ocean beneath an icy crust. This idea has led some scientists to propose that exomoons could be one of the best places to search for extraterrestrial life. In our own solar system, places like Europa, Enceladus, and Titan are considered prime candidates for life because they have liquid water and complex organic chemistry. If similar moons exist around exoplanets, they could be just as promising, if not more so, because they may have had stable conditions for billions of years. If an exomoon had the right conditions for life, it would raise fascinating questions about the potential for complex ecosystems beyond Earth. Could an exomoon have its own evolutionary pathways, separate from those of its host planet? Could it develop unique forms of life that adapt to its specific environment? If an exomoon orbited a gas giant with a thick atmosphere, could it experience periodic eclipses where the planet blocks its star, creating extreme shifts in temperature and lighting? How would life adapt to such conditions? These are the kinds of questions that make the search for exomoons so exciting. We're not just looking for another moon, we're looking for entirely new kinds of worlds, with their own unique climates, geologies, and potentially even biospheres. The discovery of an exomoon would be one of the most groundbreaking findings in modern astronomy, comparable to the discovery of the first exoplanet, or the first evidence of an exoplanetary atmosphere. Right now, astronomers are continuing to refine their search methods, using data from the Kepler Space Telescope, Hubble, and JWST. The biggest challenge is distinguishing the signal of an exomoon from all the other noise in the data. It requires extremely precise measurements and careful analysis to confirm that a dip in brightness is caused by a moon and not some other factor. One of the most promising techniques for detecting exomoons in the future is the use of next-generation telescopes, such as the upcoming Extremely Large Telescope, ELT, and the Habitable Worlds Observatory, HWO. These telescopes will have much greater sensitivity, allowing astronomers to detect smaller and more distant objects with greater precision. But even with these advances, the search for exomoons remains one of the greatest challenges in modern astronomy. It requires patience, precision, and sometimes even a bit of luck. But history has shown that some of the most profound discoveries in science come from the most difficult searches. If the first confirmed exomoon is discovered within the next few years, it will be a game-changing moment. It will prove that moons are not unique to our solar system and that they may be just as diverse and abundant as planets themselves. It will also open the door to new questions. How many exomoons are there? What kinds of environments do they have? Could some of them host life? The search for the first exomoon is not just about finding a new celestial object. It's about pushing the boundaries of our understanding and revealing the hidden complexity of the universe. Every time we discover something new beyond our solar system, we get a little closer to answering the ultimate question: how unique is Earth, really? And if moons can be as diverse and dynamic as planets, what else might be out there, waiting to be discovered? The search for the first exomoon is one of the most ambitious and intricate challenges in modern astronomy. Unlike planets, which can be identified through clear and repeated patterns in transit data, exomoons introduce a layer of complexity that makes detection far more difficult. The small size of a moon relative to its host planet means its effect on light curves is subtle, often buried beneath the natural variations in a star's brightness or the much stronger signal of the planet itself. Even when an anomaly is detected, astronomers must meticulously rule out all other possible explanations before they can even consider the possibility of an exomoon. One of the most promising candidates for an exomoon is Kepler-1625b I, an object orbiting the gas giant Kepler-1625b, located about 8,000 light-years away. The potential detection of this moon came from an unusual transit pattern. Kepler-1625b showed a transit event with a peculiar asymmetry, as well as an additional dip in brightness that followed the main planet's transit. This hinted at the presence of a large, Neptune-sized moon orbiting the gas giant, an unexpected finding given that no moons in our solar system come close to that size. However, even with follow-up observations using the Hubble Space Telescope, the data remains inconclusive. While the findings are intriguing, astronomers still cannot definitively confirm that Kepler-1625b I is an exomoon rather than a statistical anomaly or an effect caused by other astrophysical factors. The challenges in detecting exomoons extend beyond mere observation. Even if a telescope detects an irregularity in a transit event, the possibility of misinterpretation is high. Stellar activity, instrumental noise, or even interactions with other planets in the system can create false signals that mimic what a moon might produce. This means that any potential exomoon candidate must be scrutinized using multiple observations, models, and independent analyses before it can be accepted as real. But why do astronomers believe exomoons must exist if they haven't been confirmed yet? The logic is based on the simple fact that moons are incredibly common in our own solar system. Earth has its moon, Mars has Phobos and Deimos, Jupiter and Saturn have entire systems of moons that rival planetary systems in their own right, and even some asteroids have tiny natural satellites. If moons are so abundant here, it would be extraordinarily unlikely for them to be absent around exoplanets. In fact, the processes that form planets, whether through accretion, capture, or impact events, should naturally lead to the formation of moons as well. The consequences of confirming an exomoon extend far beyond simply adding another category of celestial bodies to our list. Moons play crucial roles in planetary systems, influencing tides, stabilizing axial tilts, and even potentially contributing to habitability. If exomoons are as common as we suspect, they could be key players in the search for life beyond Earth. In fact, some scientists argue that habitable exomoons might be even more numerous than habitable exoplanets. While planets in the habitable zone of their stars are often the primary focus of astrobiology, moons orbiting giant planets could also exist in stable, life-friendly conditions. A large exomoon with an atmosphere, liquid water, and the right chemical composition could be just as capable of supporting life as an Earth-like planet. One of the most fascinating aspects of exomoons is the possibility that they might be tidally locked to their host planets, just as our moon is locked to Earth. This would mean that one side of the exomoon would always face its planet while the other faces away. The consequences of this kind of tidal locking could be dramatic, affecting everything from climate patterns to potential weather systems. If an exomoon orbits a gas giant with a thick atmosphere, it might experience periodic eclipses, where its host planet blocks the light from the star for extended periods. This could result in wild temperature swings, with long periods of cooling followed by sudden warming when the star reappears. Another fascinating aspect of exomoons is their potential geological activity. In our solar system, we see examples of moons that are far from static. Jupiter's Io is the most volcanically active body in the solar system, with hundreds of volcanoes erupting due to intense tidal forces from Jupiter. Europa, another of Jupiter's moons, has a subsurface ocean beneath its icy crust, maintained by similar tidal heating. Saturn's Enceladus shoots plumes of water vapor into space, suggesting the presence of a hidden ocean below its surface. If exomoons around distant exoplanets experience similar tidal effects, they could harbor underground oceans or even volcanic activity, providing the necessary energy for life to develop. One of the most mind-bending possibilities is that some exomoons could themselves have smaller moons, what astronomers call moonmoons, or submoons. In theory, if an exomoon is large enough and has a strong gravitational pull, it could host a smaller object in orbit around it. While no moonmoons have been discovered in our solar system, the idea is not physically impossible. If we were to detect an exomoon with a smaller satellite of its own, it would raise incredible new questions about the nature of moon formation and the stability of multi-tiered satellite systems. Looking ahead, the future of exomoon hunting is likely to be shaped by new advancements in telescopes and observational techniques. The James Webb Space Telescope, JWST, is already revolutionizing our understanding of exoplanets by detecting their atmospheres in greater detail than ever before. While JWST's primary focus is not exomoons, it could still provide valuable insights, particularly for large moons with detectable atmospheric signatures. Upcoming missions such as the European Space Agency's Plato, planetary transits and oscillations of stars, and NASA's Habitable Worlds Observatory will further refine our ability to detect smaller celestial bodies around distant stars. One of the most exciting future methods for detecting exomoons involves gravitational microlensing, a technique that uses the warping of spacetime by massive objects to magnify distant celestial bodies. If a planet with a moon passes in front of a background star, the light from that star could be distorted in a way that reveals both the planet and its moon. While this method is challenging and requires precise alignment, it could allow astronomers to detect exomoons in systems that are otherwise too distant to observe directly. Despite the immense challenges, the search for the first exomoon is a quest that will continue to push the boundaries of human knowledge. Every time we have discovered a new category of celestial objects, exoplanets, rogue planets, super-Earths, we have had to rethink our assumptions about how planetary systems form and evolve. The discovery of an exomoon will be no different. Whether it turns out to be a small rocky body orbiting a gas giant or a massive, Neptune-sized moon in an unexpected orbit, its existence will redefine what we know about the diversity of worlds beyond our solar system. And once we find the first exomoon, the real journey begins. Because if we find one, that means there are many more out there. It will open the door to an entirely new field of study, with astronomers cataloging and classifying exomoons just as they do exoplanets today. It will also bring us closer to answering some of the most fundamental questions about the universe. How common are Earth-like worlds? Could life exist in places we never expected? And ultimately, how special is our own moon in the grand scale of the cosmos? The discovery of the first confirmed exomoon would not just be an astronomical milestone. It would reshape our understanding of planetary systems and potentially even the conditions for life beyond Earth. Every major discovery in space science has led to a cascade of new questions and possibilities, and an exomoon would be no exception. If we find one, how many more are out there? Do they come in the same varieties as the moons in our solar system, or are there entirely new types we haven't yet imagined? And could some of these distant moons be habitable? To put the challenge into perspective, think about the vastness of space and the sheer difficulty of detecting something as small as an exomoon. Planets, even those light years away, can be spotted because of their influence on their host stars, whether through the slight dimming they cause as they pass in front of their star transit method, or the tiny wobble they induce through gravitational pull, radial velocity method. Moons, on the other hand, are much trickier. Their signal is weaker, their transit effects are often drowned out by the much larger presence of their host planet, and their gravitational influence is subtle at best. Detecting an exomoon is like trying to hear a whisper in a stadium full of shouting fans. It requires incredibly precise instruments, meticulous data analysis, and a deep understanding of all the possible alternative explanations for what's being observed. Take Kepler-1625b I, the leading candidate for an exomoon, as an example. The 2017 announcement by astronomers David Kipping and Alex Tichy generated a flurry of excitement and skepticism in the scientific community. They had analyzed data from NASA's Kepler Space Telescope and noticed something strange. Kepler-1625b, a gas giant about the size of Jupiter, seemed to have an irregular transit signal. There was a secondary dip in the light curve, as if another object was passing in front of the star shortly after the planet itself. This anomaly, coupled with a slight deviation in the timing of the planet's transit, suggesting gravitational influence from another body, made Kipping and Tichy suspect that they might be seeing the first evidence of an exomoon. However, the scientific process is slow, careful, and rigorous. Extraordinary claims require extraordinary evidence, and despite the promising data, confirmation remained elusive. In 2018, they followed up with observations from the Hubble Space Telescope, hoping to get more precise measurements. The results were intriguing but inconclusive. While the data still seemed to support the existence of a moon, it wasn't definitive enough to be called a discovery. Some scientists pointed out that the anomalies could be caused by instrumental noise, systematic errors, or even the natural variability of the star itself. This is one of the biggest obstacles in the search for exomoons, distinguishing a real signal from all the possible confounding factors. Stars are not perfectly steady beacons of light. They fluctuate, pulsate, and produce irregularities that can sometimes mimic the effects of a transiting moon. Even our instruments, as advanced as they are, have their own imperfections and limitations. When looking at data from thousands of light years away, even the smallest noise can introduce doubt. Despite these hurdles, the search continues, and with every new observation, astronomers refine their techniques and improve their models. One promising method for detecting exomoons involves looking at how a planet's transit timing varies. When a planet orbits its star, it follows a predictable schedule, like a train arriving at a station at regular intervals. But if that planet has a moon, its gravitational pull can cause tiny variations in the schedule, making the planet arrive slightly early or late compared to expectations. This method, known as transit timing variations (TTV), has already been successfully used to confirm the presence of exoplanets, and scientists hope it can do the same for exomoons. Another method being explored is transit duration variations (TDV), which looks at slight changes in how long a planet's transit lasts. If a moon is orbiting the planet, its gravitational pull could stretch or compress the planet's orbit slightly, leading to subtle shifts in how long it takes for the planet to pass in front of its star. By combining TTV and TDV data, astronomers can build a stronger case for the existence of an exomoon. Gravitational microlensing is another technique that holds promise. This method takes advantage of the way massive objects warp the fabric of space-time. When a planet with a moon passes in front of a distant background star, the light from that star bends around the system, magnifying it in a way that can reveal the presence of both the planet and its moon. While this method is challenging and relies on rare alignments, it could provide another pathway for exomoon detection in the future. One of the most exciting aspects of finding an exomoon is the possibility that some of them could be habitable. In our solar system, we see examples of moons that have conditions that could potentially support life: Europa and Enceladus, with their subsurface oceans, and Titan, with its thick atmosphere and liquid methane lakes. If similar moons exist around exoplanets, they could be prime candidates in the search for extraterrestrial life. The concept of a habitable exomoon opens up a whole new realm of possibilities. Imagine a massive gas giant orbiting in the habitable zone of its star, with a large Earth-sized moon covered in oceans, bathed in just the right amount of starlight. Unlike a traditional Earth-like exoplanet, this moon would have the added influence of its host planet's gravity, which could lead to unique tidal heating effects, geological activity, and even exotic weather patterns. Some scientists believe that habitable exomoons might outnumber habitable exoplanets, simply because gas giants are more common than terrestrial planets, and where there are gas giants, there are often moons. If an exomoon is tidally locked to its planet, meaning one side always faces the planet while the other faces space, it could have dramatically different environmental conditions depending on location. The side facing the gas giant might be in perpetual twilight, with light reflecting off the planet's clouds, while the other side experiences full day-night cycles from the distant star. This kind of unique environment could create never-before-seen ecosystems if life were to evolve there. While current technology limits our ability to directly confirm exomoons, the future is bright. The James Webb Space Telescope, JWST, is already providing unprecedented detail on exoplanet atmospheres, and while its primary mission isn't exomoons, it could still provide valuable data for their detection. Future missions, such as the European Space Agency's Plato and NASA's Habitable Worlds Observatory, will push the boundaries even further. In the next few decades, we might not just detect exomoons, we might start classifying them, studying their compositions, and even identifying those that could be habitable. The search for the first exomoon is one of the most challenging but rewarding frontiers in astronomy. It requires patience, precision, and an openness to rethinking what we know about planetary systems. If and when we finally confirm the existence of an exomoon, it will be a groundbreaking moment, one that will remind us that the universe is far stranger and more complex than we ever imagined. And once we find one, the floodgates will open. We'll begin to uncover a hidden population of worlds we never knew existed, pushing the boundaries of what we thought was possible in the cosmos. The search for exomoons is more than just an astronomical curiosity. It's a quest that could redefine our understanding of planetary systems, habitability, and even the origins of life itself. The implications of finding a confirmed exomoon are staggering. It would mean that moons, like planets, are not just confined to our solar system. It would confirm that the complex gravitational and evolutionary interactions we see between planets and moons here in our own cosmic backyard are happening all across the universe. And if some of these moons are habitable, it could change the way we think about the search for extraterrestrial life. One of the biggest challenges in confirming an exomoon is the sheer difficulty of distinguishing its signal from that of its host planet. Unlike planets, which cause a relatively large and obvious dip in a star's brightness when they transit, exomoons are much smaller, making their effects much more subtle. They don't just transit the star, they also orbit the planet, leading to irregular timing variations, shifting shadows, and complex interactions that are incredibly hard to untangle from telescope data. Kepler-1625b I remains the strongest candidate for an exomoon, but its case remains unproven. When the Hubble Space Telescope followed up on the initial Kepler findings, the data continued to suggest that something unusual was happening, but the results were not conclusive enough to declare it an exomoon discovery. Scientists had to contend with the fact that Hubble's data was limited. Only a single transit was observed, making it difficult to rule out alternative explanations. The possibility remains that the signals could be artifacts of instrumental noise or the natural variability of the star itself. Despite these uncertainties, the potential characteristics of Kepler-1625b I remain fascinating. If it exists, it would be a Neptune-sized moon orbiting a Jupiter-sized gas giant, something unlike anything in our solar system. It challenges our understanding of how moons form. Our current models suggest that moons tend to form around planets in specific ways, either through co-formation, where the planet and moon form together from the same disk of material, capture, where a wandering body is pulled into orbit around the planet, or impact events, where a large collision creates a debris disk that eventually coalesces into a moon. As we believe happened with Earth's moon. A Neptune-sized exomoon around a gas giant is difficult to explain under these models, suggesting that either our theories of moon formation need revising, or that this system evolved under unique circumstances we have yet to understand. The uncertainty surrounding Kepler-1625b I highlights the need for better observational techniques and next-generation telescopes. The James Webb Space Telescope, JWST, with its advanced infrared capabilities, could provide new insights by observing exoplanetary transits with even greater precision. If JWST were to observe multiple transits of Kepler-1625b, it could help determine whether the anomalies observed by Kepler and Hubble are truly the result of an exomoon, or if they stem from something else entirely. Beyond JWST, future telescopes such as the Habitable Worlds Observatory and next-generation space telescopes will push the boundaries of what we can detect, allowing astronomers to study exoplanets and their potential moons in even greater detail. Another promising approach in the hunt for exomoons is the study of planet-star interactions. When a planet orbits a star, it causes a tiny wobble due to the gravitational pull between the two bodies. If a moon orbits the planet, it can create additional, smaller wobbles in the planet's movement, which in turn affects the timing and shape of the transit signal. This method, known as transit timing variations (TTV) and transit duration variations (TDV), has been crucial in identifying exoplanets and could prove just as useful in finding exomoons. Microlensing is another method that holds promise for detecting exomoons. This technique relies on the gravitational bending of light caused by a foreground object passing in front of a distant background star. If a planet with a moon moves in front of a star, the light from that star is temporarily magnified, revealing details about the objects causing the lensing effect. While this method relies on rare alignments, it could provide another pathway to confirming exomoons in the future. The potential for habitable exomoons is one of the most exciting aspects of this search. In our solar system, we have moons that may harbor life beneath their icy shells. Europa, Enceladus, and Ganymede are all prime candidates due to their subsurface oceans, which remain liquid due to tidal heating from their host planets. If similar moons exist around exoplanets, they could be some of the best places to look for life beyond Earth. Imagine a habitable exomoon orbiting a gas giant in the habitable zone of its star. Such a world could experience unique environmental conditions, strong tidal forces that drive volcanic and geological activity, dynamic atmospheres influenced by both the star and the gas giant, and a complex interplay of day-night cycles depending on its orbital characteristics. Some exomoons could even experience double sunsets, one from their host star and another from the reflection of light off their parent planet. Tidal heating, a process that keeps some of our own solar system's moons geologically active, could play a crucial role in the habitability of exomoons. This occurs when gravitational forces from a planet stretch and compress a moon, generating heat through friction. On moons like Europa and Enceladus, this process keeps liquid water beneath the surface, creating conditions that could support microbial life. If a similar process is happening on exomoons beyond our solar system, it could mean that life has many more opportunities to exist than we previously thought. One of the biggest open questions in exomoon research is whether such moons could have atmospheres. In our solar system, Titan, Saturn's largest moon, has a thick atmosphere composed mainly of nitrogen, with liquid methane lakes and weather patterns. If exomoons around exoplanets have similar atmospheres, they could host a wide range of climates, potentially even ones suitable for life as we know it. The search for exomoons is still in its infancy, but every year brings new advancements that bring us closer to a discovery. The challenge is enormous, but the rewards could be even greater. Finding a confirmed exomoon would not just be a scientific achievement, it would be a reminder that the universe is full of hidden wonders waiting to be uncovered. And once we find one, we will begin to understand just how common or rare these celestial bodies truly are. As technology advances and our observational techniques improve, we stand on the brink of an era where exomoons may become a regular part of our astronomical discoveries. The first confirmed exomoon is out there, waiting to be found. It's just a matter of time before we finally see the evidence that proves these elusive worlds exist. And when we do, the floodgates will open, revealing a hidden population of moons that could reshape our understanding of planetary systems, habitability, and the potential for life beyond Earth. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.